Greetings of the day to you all. I welcome you all to Day 2 of Science Academies 5-day International Online Lecture Workshop organized by Department of Physics, St. Philomena's College, Mysore. We have with us today Professor M.V.N. Murthy, retired professor, Theoretical Physics, the Institute of Mathematical Sciences, Chennai. Professor M.V.N. Murthy retired from the Institute of Mathematical Sciences in 2013. He had his early education from Central College, Bangalore and University of Mysore. He got his PhD from the University of Mysore and was a visiting fellow at TFR, Mumbai. He was a postdoctoral fellow at the Department of Physics and Astronomy at McMaster University, Canada, and also at the Institute of Theoretical Physics of the University of Regensburg, Germany. His research interests have centered around high energy physics, semi-classical physics, and statistical mechanics. I welcome you, sir, on behalf of the organizers. Over to you, sir.
Thank you very much. So let me share the screen.
Yes, sir.
Okay. Okay. So good afternoon, everyone. Thank you very much for inviting me to this workshop to talk about supernova and neutrinos. Actually, I will not be talking about supernova and supernova that much. Rather, I will talk about some mechanism which is obeyed, some property which is obeyed by the neutrinos and the origin of that property by looking at other areas of neutrino detection. So that's why this is titled as Disappearing Neutrinos, Neutrino Oscillations. And the idea of neutrino oscillations will be later used by other speakers. So here is something about the importance given to this area. Hello?
Carry on, sir. Okay, sir, you carry on, sir.
Okay. Yeah. Please mute your mic if you have not done it. So this is a list of all the Nobel Prize winners in recent times. And specifically, it's neutrino physics. Fred Reiners got the Nobel Prize in 1995 for the discovery or detection of very first detection of the neutrino. And Davis and Koshiba got the Nobel Prize in 2002. They shared the Nobel Prize. Davis for the detection of neutrinos from the sun, and Koshiba for the detection of neutrinos from supernova 1987A. And few years ago, in 2015, Professor Kajita and Professor McDonald from Japan and Canada, respectively, got the Nobel Prize for their discovery of neutrino mass and neutrino oscillations. I will specifically focus on this neutrino mass and neutrino oscillations and the work of Professor Kajita and his collaborators, Professor Art McDonald and his collaborators in Japan and in Canada. So here is the outline of the talk. There will be a bit of repetition. I hope you don't mind. Maybe there are some people who are new today, so for them it may be very good. However, I will condense the introduction so that there is not too much of repetition. So here is the outline of the talk. I'll talk a little bit about the neutrinos and their place in the standard model. When we say standard model, this is the standard model of high energy physics. And then I will talk to you about a problem. First, it's no more a problem. The solar and the atmospheric neutrino problem. This is what I called as the disappearing neutrino. And that appeared in the detection of solar neutrinos, that means neutrinos from the sun, and the neutrinos which are produced in our own atmosphere. And then I talk about resolution and a new mystery which has come. And the last part of it is about INO in context. I may not have time to talk. The resolution and the new mystery which is arising from that, I will talk about it tomorrow. Today, the first three topics I have mentioned are the focus of my talk. This you saw yesterday. Neutrinos are everywhere. In fact, it's the second most abundant particle in the universe after the photon. We know a lot about photon and its properties. We know almost everything. In contrast, even though neutrinos are ubiquitous, we do not know much about their properties. In fact, we do not even know what their absolute masses are. We have some information about the difference of masses, but not about the absolute masses of these neutrinos. Nevertheless, they are there everywhere. They come from the sun, and as you heard yesterday, they are produced during the collapse of massive stars, which are about 10 times or more massive than the sun. And for the first time, the neutrinos from such a collapsing star was sighted in the Large Magellanic Cloud, and the neutrinos were detected in 1987. That's why it's called SN 1987. Both in Japan and several other laboratories around the world. Then you have the cosmic Big Bang. You heard about it yesterday. Then astrophysical accelerators. These are still not very clear. And then the natural radioactivity of the Earth. You know that there are radioactive elements which can be mined from the Earth. And they also produce neutrinos. And then there is nuclear reactors which produce. These are man-made facilities. And then particle accelerators and our own Earth's atmosphere, the cosmic rays coming from outer space, when they hit the air molecules, they produce neutrinos. So the sources are there everywhere, and you will be surprised that as human beings, we also produce neutrinos. There is a little bit of potassium, radioactive element of potassium in our body, and that produces this neutrinos, very low energy neutrinos. So we human beings are also sources of neutrinos. Of course, these neutrinos come in various energies. They have a whole spectrum. This also Professor Amol Digge showed you yesterday. Starting from the cosmological neutrinos, which are very low energy, fractions of electron volts to micro electron volts. Then you have the solar neutrinos, which are in the range of MeV, or millions of electron volts. So electron volt is a unit of energy which we use in high energy physics. And you know the binding energy of an atom is of the order of electron volts. So you can think of millions of electron volts as something which is much larger than the binding energy of the atom, a million times of the order large. Then you have the supernova burst neutrinos. That will be the focus of Professor Amol Digge's talk. And then you have reactor antineutrinos, background from world supernova, and then the atmospheric neutrinos, which are in the GeV range, that is 10 to the power 9 electron volts, as opposed to solar neutrinos, which are millions of electron volts. So here is a neutrino timeline. It gives the history in a nutshell. It was proposed by Pauli in 1930s, in the beginning of 1930s. They had a problem in the decay of tritium, and they had to balance the energy and the angular momentum in this reaction. And without the neutrino, you cannot balance it either. If neutrino is not there, then because it's a two-body decay, electron will come out with a well-defined energy and not a continuous range of energies. But if it's a three-body decay, then the electron would come out with a continuous range of energies because it shares it with the neutrino. So based on this experimental data, Pauli proposed that there should be another particle because the electron has continuous energy in this beta decay. But it took a long time to detect these neutrinos, in fact, the antineutrinos. In 1956, it was experimentally detected. In this interaction, nu E bar hitting a proton going to a positron and a neutron, and this source of antineutrino was a reactor, and this experiment was done by Reines and Cohen and their co-workers, and Professor Reines got the Nobel Prize in 1995 for this. There were more neutrinos. This is one type of neutrino, which we call as the electron type of neutrino, which is produced in interactions which involve the emission of charged particle, electron. Similarly, when a charged particle muon is involved in a reaction, sometimes associated with it, there is a neutrino. And that is called as the nu mu. And that was detected in 1962 by Lederman. And there was another neutrino, nu tau, which was confirmed as late as 1999. But we knew more or less that it has to be there because corresponding to every charged lepton, electron, muon, and tau, it was expected that there should be associated neutrinos. And importantly, in 1965, atmospheric neutrinos were for the first time observed in nearby Kolar goldfield by a collaboration of scientists from Tata Institute, Osaka, and the Durham group. 1967, beginning of the solar neutrino experiment at home state mines by Davis. I'll talk about this a little bit. And then 1987 was the observation of neutrinos from Supernova SN 1987A. This is by Koshiba et al. And in 1998, evidence of oscillation and non-zero neutrino mass. This is from Super K detector in Japan. And 2002 was the confirmation of the oscillation and the standard solar model. This was done at the Sudbury Neutrino Observatory in Canada. And most importantly, more recently, 2011, the last mixing angle, I'll mention what this is. Last mixing angle was measured in the Diabei, China. Diabei experiment in China and Reno in Korea. This is about the neutrino timeline, and there are many more experiments to come, planned, and they will be coming. So, why neutrinos are in fact the reason why we all exist. There are, as I said, there are three types of neutrinos. They are extremely weakly interacting, and stopping distance at a few MeV is of the order of light years. This was mentioned yesterday, whereas for alpha, beta, and gamma rays that you are familiar with, it is of the order of tens of centimeters. Properties of neutrinos may be responsible for matter-antimatter asymmetry, and without this asymmetry, the universe will not exist as we know. And the production of heavy elements would not be possible without neutrinos and weak interactions. And in fact, such elements are produced in the supernova at the last stage, and they are produced in the core of heavy stars and dispersed all around galaxy during the explosion. They hold the key to the origin of the solar system and in fact to the Earth itself. And the energy production in Sun is through fusion. And that's true of any other star also. And that would not be possible without weak interactions and neutrinos. Because of their feeble weak interactions, the experiments require huge detectors where by making it huge, you are increasing the number of targets, and you place it deep underground to escape the huge background cosmic ray that you find on the surface of the Earth. So here are some underground laboratories around the world. There are some at lower levels. At Kamioka, the depth is around 1,000 meters of rock. There's Gran Sasso in Italy, which is 1,300 meters. These Buxton and Mont Blanc were operating earlier. And then Sudbury Neutrino Observatory is one of the deepest at 2.1 kilometers below the ground. And then you had the KGF underground laboratory, which doesn't exist anymore. And that was the deepest underground laboratory in the world when it was operating. It went almost up to 3 kilometers below the surface of the Earth. Please stop me if you want to ask any question. Unmute your mic and you can ask. I'm not able to see the chat. I don't know why. So I may not be able to see the questions on the chat. So you unmute the mic and you can stop me at any time and ask. Okay. So let us go about these issues one by one. The first is the solar neutrino puzzle. So what is this puzzle? It has a long history. In fact, the puzzle began more than 150 years ago during the time of Darwin and Kelvin. So here is a brief history of the problem. You can ask the question asked by Darwin, Charles Darwin in around 1850s. How old is the life on Earth? There is no life without energy from the sun. So how old is the sun? Must have existed longer than life on Earth, obviously, because all our energy which sustains life on Earth comes from the sun. Then what powers the sun? How does the sun produce vast amounts of energy to support life on Earth and everything else? Now, these are questions which challenged physicists, chemists, geologists, evolutionary biologists since the middle of 19th century. In 1859, Charles Darwin made a crude estimate of the age of the Earth, approximately about 300 million years. The reason why he wanted 300 million years was that this was long enough for natural selection to have produced a huge range of species that exist on Earth. So his estimate of 300 million years therefore implies, since life has existed as long as 300 million years, that sun must have been radiating energy over a period of at least 300 million years, if not longer. But then there was a controversy. The biologists and the geologists wanted hundreds of million years for reasons which the scientific facts from their fields needed. And the physicists were also looking at this problem. Mayer and Watterson and Helmholtz suggested the origin of solar energy as a conversion of gravitational energy into heat. William Thomson, who became Lord Kelvin, a very influential physicist of 19th century, first suggested that the sun's energy might be produced by the impact of meteors falling on its surface. Later, he modified it, and his conjecture was based on astronomical evidence, and he modified it and came to the conclusion that gravitational energy, if that is the reason for all of solar energy that we receive, then it can only last about 30 million years. On the other hand, Darwin wanted 300 million years to have the evolution that evolution of life as he was looking at it, whereas Kelvin was estimating the total life of sun to be about 30 million years based on the energy calculation. So in fact, Kelvin's authority was so overwhelming that Charles Darwin removed any mention of 300 million years in the second edition of his book, his epic on the origin of the species. Now, how did Kelvin get 30 million years? Now, here is the back of the envelope calculation. This is something we physicists all the time do, and it's a good habit to keep it just to get orders of magnitude estimate. So, how much gravitational energy is there in the sun? That you can just compute the gravitational potential energy of the sun, assuming the radius of the sun and the mass of the sun. So, which is gm squared by the radius. Okay. And if you calculate it in units of arcs, it comes to about 4 into 10 to the power 48 arcs. That's the total gravitational potential energy of the sun. Now, what is the luminosity of the sun? Luminosity is the energy radiated every second. So from sun, we receive about 4 into 10 to the power 33 arcs per second. Every second as we measure it. So therefore, you just divide the total energy by the luminosity, then you get the number of seconds for which this energy can last, and you can see 10 to the power 48, 10 to the power 33, just order of magnitude estimate gives you 10 to the power 15 seconds, and 10 to the power 15 seconds is the 30 million years that Kelvin was talking about. So the physics of the day dictated that sun would radiate only for about 30 million years, but you needed a new source of energy, therefore, if you want to account for more than hundreds of million years, which geologists and biologists wanted. So by the end of 19th century, the problem had not been resolved. There was still a controversy between physicists, geologists, and biologists. The source of sun's energy remained a major puzzle, and you got different answers depending on whom you ask this question. So obviously, theoretical physicists, why theoretical physicists? Physicists argued that it should be tens of million years of old, and biologists wanted hundreds of million years. By 1917, the radioactive dating already estimated the age of the Earth. It's not about the sun, age of the Earth to be about 2 billion years. More accurate estimates now give about 4.5 billion years. So obviously there is something wrong with the 30 million years calculated by Kelvin. So there must be another source of energy. So what is it? So here are the early clues. First, it was discovery of radioactivity. Since during radioactivity energy is emitted, it becomes a new source of energy. It became a new source of energy. And Rutherford in 1904 thought that this may be the source of energy that one needs to explain how the sun shines. But that was not to be, because there was a problem with the temperature dependence, and astronomical observations showed that in fact it cannot be just radioactivity. And the clue came from yet another discovery of Rutherford, which is the nucleus. An atom, of course, is made up of electrons hovering around the nucleus, as you all know. And the turning point came in 1905 when Einstein derived his famous relation E equals mc squared. The mass is energy. As a consequence of the special theory of relativity, since C is such a large number and C squared appears in this equation, even a tiny amount of mass in principle can be converted into tremendous amount of energy. There was another clue that was needed, which was provided in 1920 by Aston of the mass spectrometer. He discovered the key experimental ingredient that when 4 hydrogen nuclei combine to form a helium nucleus, the helium nucleus is slightly lighter than the 4 hydrogen atoms. So that means part of the energy might have gone into creating this helium nucleus, and the rest might have been emitted. Now, Eddington in 1920 immediately realized that this could explain why the sun continued to burn for such a long time, namely the fusion of 4 hydrogen nucleus, that is protons, into helium nucleus. We will see how it comes about. The tiny mass difference may be converted into enormous energy that the sun radiates. So here is how we can do another back of the envelope calculation. To estimate the age of the sun using Eddington's arguments, he was the first one to talk about fusion. Assume about 10% of the sun's mass in the form of hydrogen. That 10% of the mass is about 2 into 10 to the power 32 grams. So let us say this is available for conversion into helium. Rest of the sun remains remains hydrogen, which is mostly hydrogen. Only in the core it's possible to convert hydrogen to helium. Let's assume that this to be about 10%, just to get an order of magnitude estimate. Then the mass difference between helium and 4 hydrogen is 0.007. This is the difference. This difference is emitted as the energy. This is an exothermic reaction that is emitted, and that therefore is 0.007 into 0.1 that comes from the solar mass multiplied by c square. Just this amount of mass will give you, converted into energy, will give you 1.26 into 10 to the power 51 ergs. Now remember, gravitational binding energy was 10 to the power 48 ergs, whereas this is 10 to the power 51 ergs. So it's 1,000 times larger than what you get from the gravitational energy of the sun. So that means it can last 1,000 times longer than the estimate of Kelvin. So he estimated it to be about 30 million years, and 1,000 times longer would be about 30 billion years. Of course, that's little overestimate. The more accurate estimate gives you the lifetime of the sun is simply the total energy by luminosity, and that's around 10 billion years. And the source of energy is indeed the fusion of the hydrogen nuclei into helium nucleus. And if indeed, here is another prophetic statement by Eddington, if indeed the subatomic energy in the stars is being freely used to maintain the great furnaces, it seems to bring us a little nearer to the fulfillment of our dream of controlling this latent power for the well-being of human race. He really meant energy from fusion, which hopefully in the next decade or so will be realized, or for its suicide. And this is he was referring to the nuclear weapons in these things. It's a very prophetic statement by Eddington. Okay, let us put all the pieces together, whatever history that we have talked about. And according to the theory of stellar evolution, and stellar evolution applies to all the stars, and sun is one example of it. The sun and the stars start out as a gas of hydrogen, the most abundant element in the universe. Due to gravitational contraction, the initial gas cloud develops a core where the enormous temperatures and densities are created. Under these conditions, in the core here, the hydrogen gradually gets converted into helium. So it is the core that plays the most dominant role in the production of solar energy. And in fact, in this process, both neutrinos and light, that's photons, are emitted. And as mentioned by Professor Amol Dige yesterday, neutrinos simply stream out of the sun's core without worrying about anything outside because they are so weakly interacting. But the photons take almost million years, 100,000 to million years to come out of this because they interact with the mantle and the convection zone, and they take a long time to come out. So in 1938, Bethe completed a detailed calculation of how the sun shines. You will hear more about it from the talk by Professor Vivek Tatha. In brief, the Bethe's theory of nuclear burning involves, in summary, the fusion of 4 protons into helium. You have to balance charge, energy, and spin everything. So therefore, this 4 helium, then 2 positrons, 2 neutrinos are emitted, along with the binding energy, which is 26.7 MeV, which comes out as light. In detail, this is a summary of a whole set of reactions which is given in this box. It starts with the fusion of two protons into a deuterium nucleus, emitting a positron and a neutrino. So this is one of the sources of the neutrinos, this reaction in the sun. Then there is another Pp plus E plus C plus going to deuterium and a neutrino. And if you look at many of these reactions, you will see in some the photons are emitted, in some of them neutrinos are emitted. So both light and neutrinos are emitted in the fusion processes inside a star. So there are many sources and we name them by the nucleus that is decaying. So for example, the neutrinos coming from boron are called boron neutrinos. Then you have pp neutrinos, and then you have beryllium neutrinos. Like that, you have many sources of neutrinos in this reaction. So any question at this stage before I proceed to the detection of these neutrinos?
I think no questions, sir.
No questions. Okay. If there are questions in the chat, please read it out to me. Okay. The chat window is not appearing on my this thing for some reason. Okay. Thank you very much. Okay. So, but all this is theory, right? Because we are talking about something which is happening in the sun, and Bethe constructed the whole set of reactions. And light can be produced by many interactions. Even when any heat is produced, you have immediately light coming out of such processes. But fusion is very special. It is occurring in the core of the sun. So what is the proof that this fusion is taking place and this whole scenario is actually correct? So from theory, we should go now to the observations where we can find out that it is actually the fusion that drives the stellar dynamics. So what is the real thing that one can detect which says it is definitely fusion? That is, as you saw in these reactions, these neutrinos are emitted only through these fusion reactions, whereas light may be emitted in many other ways. These neutrinos come through these fusion reactions, and that too specifically so-called weak interactions. Okay, so here, therefore, the proof of the pudding is in finding neutrinos. So if you can detect neutrinos coming from the sun, definitely you can say that fusion is the reason why the sun shines. So then we have found the answer to our question, which we began in 1859. So the same set of reactions that supply energy of the sun also produce neutrinos that can be detected in the laboratory. Since the neutrinos interact only weakly with matter, they are notoriously hard to detect. And the first attempts were made as early as 1960s by Ray Davies. So here is discovery and confirmation that we want to look at. So Davies and collaborators proposed this experiment sometime in 1964. And in fact, the collaborator was John Buckle, who wrote the first version of the standard solar model and revised it many times, so that by 1998 we had what is called as a standard solar model, which tells you a lot of things about the sun. It tells you the energy production mechanism, all these interactions, and also it tells you what the neutrino flux should be. I had somewhere the neutrino flux information. I must be missing it in my slides here, but that's not important at the moment. That will Professor Vivek Datar will talk more about it. So Davies and collaborator proposed this experiment. Now, as I told you before, neutrinos are notoriously difficult to detect. One, they interact very weakly compared to electromagnetic interactions and other things. They are 10 to the power minus 24 times weaker or even weaker than that. So therefore, you need large number of targets so that the probability of the interaction of these neutrinos increases. And because the interaction cross-section is so small and the probability, even when you increase by making the detector very large, the background can kill that. So how do you reduce the background? The main background on the surface of the Earth is due to the cosmic rays, the primary and the secondary cosmic rays. So one way to shield these primary and secondary cosmic rays is to go deep underground, use enough of rock cover to screen out this cosmic ray background. So most, as it was established in Kolar goldfields, if you are around 1 kilometer or up to 2 kilometers deep underground, then the cosmic ray interactions come down by a factor of million or more depending on the depth. So you can cut down the background by a factor of a million by going deep underground. And this is what Ray Davis did. He had a detector which had 600 tons of perchloroethylene, which is simply dry cleaning fluid, and it was cheap and it was available. 600 tons those days was a very large detector. Nowadays we talk about 50,000 tons. The 600 tons compared to today's detectors is puny, but for the time when Davis proposed it, it was one of the largest detectors. And he put it in a mine about 2 kilometers underground. It was also a gold mine. And these 600 tons were stored in a cylinder, as you can see here. And normal chlorine is 35 chlorine. But this perchloroethylene has a small percentage of 37 chlorine, which is radioactive. And when a neutrino interacts with this 37 chlorine nucleus, it produces a 37 argon and an electron. And as you know, the energy of these neutrinos, when we saw in the spectrum, is of the order of a few MeV. It starts from about hundreds of keVs, goes all the way up to about 10 MeV or a little more. And the electron is, in order to produce electron, which has a mass of half an MeV, the threshold here has to be at least of the order of MeVs, or a fraction of MeVs. And in fact, this is around 0.8 MeV or a little more than that. And therefore, the energy of this electron to traverse through the detector and come out is not there. The electron is simply absorbed in the detector itself. So how do you know that this interaction actually happened? So this is one of the master strokes of Davis, and is one of the really very beautiful. In fact, what he did was like looking for a needle in a haystack. Now, he looked for argon in this production of this argon in this 600 tons, which contains this 37 chlorine. Now, how do you do that? Now, you know the background, what is the percentage of argon which is already present. So you will have to do that, collect that background data. And then when the 37 argon is produced using this interaction, this will be over and above what is already present in this detector liquid. And how do you count these excess 37 argon atoms? They have an affinity to helium. So you pass helium gas through the detector, and the 37 argon atoms are flushed out of the detector and then counted. Unfortunately, the decay rate is very small. This reaction occurs about 1 in 3 days, and that is one excess argon atom is produced in 3 days. So you can see the extraordinary difficulty of this experiment. So you have to wait, but fortunately 37 argon has a long lifetime of more than 30 days. So therefore you can wait and collect many atoms and get it out. So of course, because you wait to collect these atoms. There is no information about the direction. That information which is contained in electron is lost because you are not detecting. And only total event rate above the threshold was measured. So in some sense, you measured the neutrinos from the sun using this experiment, but you only got the total number of events. You didn't get the energy spectrum or the direction. So therefore, you can also argue that how do you know it is from the sun if you don't know the direction? Okay, that was criticism was answered by the next experiment, which is a solar neutrino experiment done in Japan. This was an experiment which you saw yesterday, and what I have shown here is the Super Kamiokande detector. Earlier this is about 50,000 tons of water looked over by photomultiplier tubes all around, and you saw this yesterday. But the first experiment was a smaller experiment, which was about 2 kilotons or 2,000 tons of water on a smaller scale. And in fact, it was not designed to look at neutrinos in the beginning. In fact, the main aim of that experiment was to look at proton decay. But when proton decay, they did not see proton decay, one realized that it could also become a neutrino detector. And this is also about 1,000 meters underground. And the criticism of Davis' experiment, which I mentioned, was how do you know that the neutrinos that he observed, neutrino events that he observed, were indeed from the sun? So this was answered by Koshiba, Totsuka, and collaborators in 1986, followed by Super Kamiokande experiment, which used a tank of water to detect neutrinos. How do they detect neutrinos? They detect neutrinos by elastic scattering of neutrinos on water. So if there is a nu E which is coming and hitting an electron in the water molecule, then it scatters off that and knocks out the electron. And this electron, which is knocked out by energy transfer from the neutrino, carries the information about the direction of the incoming neutrino, which is this. So if the neutrino is coming from the direction of the sun, that information is carried by this electron. So we say that this reaction is directional. It is the probability or the cross section for this reaction is peaked in the forward direction. So once they could establish that these neutrinos are coming from the direction of the sun, as observed through this reaction, then we could identify that these are indeed neutrinos which are coming from the sun. And the energy of the electrons has to be in this experiment a little more than 5 MeV. That means about 10 times the mass of the electron. That makes it relativistic. And when the electron is relativistic and it passes through a medium, it emits what is called as the Cherenkov light that you can see here. It's a blue light which you saw yesterday in one of the talks. And this Cherenkov light is emitted in the form of a cone, and the axis of the cone is the direction of propagation of this electron. Now, once you know the direction of the propagation of the electron, then the cross section which you can measure or which you already know is peaked in the forward direction. So if you know the direction of the electron, then you can say that the neutrino direction is within, for more in almost all the cases, it is within, in fact 95% of the cases, it is within 15 degrees from the direction of the electron. So with that error, you can say that that is the direction of the neutrino, and you work backwards and see where it is coming from, and you can identify it with the sun. So yesterday you saw the picture of the neutrino sun and the optical sun, which Professor Amol Dighe showed. And optical sun was very nice, round, circular disc, crimson and very beautiful color. Whereas the neutrino disk was a bit fuzzy. That fuzziness partly comes from the fact that we cannot precisely say what the direction is, but it is about 15 degrees plus or minus. Okay. Now,
Hello.
Hello, yes. Is there a question?
No, no, sir. Some disturbance from the student, I
Okay,
think.
okay.
Sorry, sir. Sorry, sir. Sorry for
No,
that.
no, no, no problem. Okay. So then I just told you about Davis's experiment, and now I just told you about this experiment in Japan, Kamioka experiment. In fact, earlier it was known as Kamiokan Day, and the last NDE was referring to nucleon decay experiment, Kamioka nucleon decay experiment. I think now they have dropped it and it's simply called Kamioka. And the bigger detector is called the Super Kamioka. Now, in Homestake mine, in the Davis experiment, he detected the neutrinos, but based on the flux calculation of the standard solar model of Bakal, he should have seen 3 times more the number of events than he actually observed in the Homestake experiment. It's 0.33. That means the ratio of observed events to the events expected from the flux calculated using the standard solar model is actually 1/3. Okay. Now, of course, since there was a doubt about the direction of the neutrinos, you waited for Kamioka experiment to confirm that there is really some deficit. So, but Kamioka experiment also found that they only see about 54% of the neutrino flux that is coming from the sun. So, in both experiments, what is expected and what is observed shows a substantial deficit, and this deficit seems to be different. Homestake mine sees 1/3, Kamioka experiment sees about 50.5. And the two experiments had different thresholds for observation. Homestake mine had an observation which gave, the observation was based on a threshold of 0.814 MeV, whereas Kamioka, because they had to observe the relativistic electrons, it was about 7.5 MeV. This was improved. Kamioka result was improved by Super K by putting a much larger detector, about 25 times larger than the Kamioka detector. And they also found in the improved detector a ratio which is 0.465. They reduced the threshold to 5.5 MeV from 7.5. Nevertheless, they found a deficit and it did not agree with the number of events estimated using the solar neutrino flux as given by the standard solar model of Bakal. There was another experiment, I haven't talked about it. This is called the radiochemical experiment, SAGE and GALAX. There are two experiments actually. These are radiochemical experiments where they can only count the total number of neutrino events and not look at the direction and spectrum. And they found about 60% of the events from the expected number of events compared to the expected number of events, though the threshold is 0.233 MeV. It had the lowest threshold and it observed the least amount of deficit. Then the next threshold is 0.8 and there you observed 1/3 and you observed slightly better results, better increased events in Super K, even though the threshold was larger. So two factors you must remember in this table. One, that all experiments saw a deficit of neutrinos compared to the predictions of the standard solar model, and they are all energy dependent. They depend on the threshold. They have different thresholds. So therefore, even though they may have some common region of observation in the energy spectrum, they also have their own special regions in energy, which is not probed by other experiments. So this is very important. So we have seen the neutrinos, but we don't agree with the standard solar model. So there's a new mystery now. The experiments have detected unambiguously the neutrinos produced in the center of the sun. Their detection proves directly that the source of energy that the sun radiates is the fusion of hydrogen nuclei in the core. So the debate, which began in 19th century between physicists and biologists and geologists, has been settled. The source of energy is fusion because we have detected neutrinos from the sun by even identifying their energy and direction. So it is now known from detailed calculation that the age of the sun is about 5 billion years. And based on the energetics, you know that it is likely to last about 9.5 billion years. So its sun is middle-aged at the moment. We also now know that the detailed composition, temperature distribution of the sun, and there is an accepted standard solar model which was developed for many times over by John Bacall and his collaborators. But there's a new mystery. The mystery is, while the neutrinos from the sun have been detected, we are sure about it, and we know it is Bethes scenario should be working, but nevertheless the number of neutrinos which are emitted at the source and the number detected do not match. Therefore, the numbers we calculate using Bethes scenario do not agree with the experiment. So we have less than half the expected neutrino flux detected. So what happened to the other half or slightly more in one of the experiments? Where are these neutrinos? After all, neutrinos are fermions. Their number is conserved unless they get annihilated when they meet their own antiparticle. But propagation from sun to the earth is almost through vacuum. So their number should remain the same. So if we are seeing less, what is the problem? Are we seeing less because our standard solar model is wrong? Which cannot be correct because standard solar model explains so many other things like luminosity of the sun and other things. So if you say standard solar model is wrong, we have to reduce the neutrino flux. You cannot reduce the neutrino flux alone. You will have to reduce all other things, including the luminosity. I mean, you are not going to say that sun is only half luminous than what we see. Then you will have to explain where the other half is coming from. So there is a contradiction of sorts here. We seem to know so much about the sun now by other measurements that we cannot change the accepted standard solar model. So there must be some other reason to explain this deficit that we see in the detected neutrino flux. Now remember, I have always used, as long as I'm talking about solar neutrinos, nu E. You know that there are three flavors of neutrinos, nu E, nu mu, and nu tau, corresponding to electron, muon, and tau. They are the neutral partners of these leptons. So there are other types of neutrinos, but as far as solar neutrinos are concerned, the only relevant flavor is the electron neutrino. Just as in a reactor, the relevant neutrino is an anti-electron neutrino or nu E bar. Now, this problem is not exclusive to solar neutrinos. There is something else that is happening. There are neutrinos coming from other sources, as we saw, and these come from our own atmosphere, and their spectrum is very different from the spectrum of energy that you see in the case of solar neutrinos. You have to remember that the solar neutrinos, the energy spectrum is few hundred keV to all the way to about tens of MeV. I mean 10 MeV or little more than 10 MeV. In fact, the maximum is around 18 MeV. So it is in that range. Okay. Now we are going to shift to the observation of neutrinos, which are at least 1,000 times more energetic than the solar neutrinos. And these are atmospheric neutrinos. Okay, how do they come? These closer home, cosmic rays, which are mainly protons, they are impinging on our Earth all the time. In fact, they interact with our atmosphere. We don't know where they come from, But cosmic ray energies, like you saw yesterday in the neutrino energy spectrum from all sources, cosmic ray energy spectrum also goes from fractions of electron volts to almost about 28 to 30 orders of magnitude. A very extremely high energy cosmic rays whose energy units I cannot specify, much more than GeV or TeV energies have been observed. And these cosmic rays, we don't know their source, but they are there. They interact with the atmosphere of the Earth all the time, all around. So you stand on any part of the Earth, you will see these cosmic rays interacting with the air molecules as shown here. And they produce what are called as secondary cosmic ray particles. And these are mainly pions. And about 15% of the time, they'll be what are called kaons. But most of the time, they are pions. And these pions decay. And when they decay, they can produce, if it's a neutral pion, pions are, they come in three avatars, pi plus, pi 0, and pi minus, three charge states. And the neutral pion goes into photons, and those photons produce pairs of electrons and positrons, all charged particles. On the other hand, this pi plus and pi minus, they decay by through weak interactions. So a pi plus may decay into a mu plus or mu minus, pi minus to mu minus and a new mu bar, and this muon, then all these are weakly interacting particles which decay. Pion decays into a muon and its antiparticle, nu mu bar, so it should be mu minus here. And this mu minus then decays into a nu mu, nu e bar, and nu e bar, and an electron. So this muon decay is a three-body decay, and this pion decay is a two-body decay. So without going into the detailed mechanism of all these things, what reaches our Earth's surface where we are standing, and in fact most of these decays occur by about 14 kilometers height, even though the atmosphere extends way beyond that, by about 14 kilometers height, since the density keeps increasing, most of these interactions and decays have occurred. On the surface, we see some muons which don't decay and come down, and the decayed pion and muons will produce this nu mu bar, nu mu, and a nu e bar. So for every electron type of neutrino, there will be two muon type of neutrinos. So if you are looking at simply flavors without worrying about whether it's a particle or an antiparticle, there will be two muon flavors of neutrinos and one electron type of neutrino flavor. 2:1 will be the ratio. Okay. Now here is the experimental result. This is from Super Kamiokande. And as you can see, neutrinos come from all directions. The Earth cannot stop it. And it is there during day, during night, because the cosmic rays are hitting the atmosphere at all times. So therefore, the neutrinos in a detector can come from the top, up, from down. Those are called as the downgoing neutrinos. And these are produced at a height of 14 kilometers above our heads. And there are also neutrinos which are coming from the other side of the Earth, or many sides of the Earth, propagating through the Earth, because the atmosphere is all around us. So therefore, these neutrinos are coming from all directions, and on every part of the Earth, every part of the surface of the Earth, they are produced by the same mechanism. So if you are looking at neutrinos coming from below or neutrinos coming from above, if there is nothing else happening and neutrinos are very weakly interacting particles, Earth cannot really stop them. I mean, the probability of stopping them is so low that most of them come through. So whether they are coming from up or whether they are coming from down, the ratio should be 2:1. There should be two muon type neutrinos for every electron type neutrinos. Or in fact, you can take the total flux of all these neutrinos and see what is happening when they are coming from below and when they are coming from above. So here is the data. This part, the right hand side, the data is all these red pluses, and this blue curve is the expected number of events by the calculated neutrino flux. This blue curve is the one which is expected. Forget about, don't look at this green. I'll come back to it a little later, probably tomorrow. Just look at this red data points and this blue curve. So for all the downward going neutrinos, so this is actually an angle. At this stage, it is vertically downwards. At this stage, it is coming at an angle. And at this stage, it is coming horizontally like this. And here it is coming through the Earth's surface. And here it is coming from vertically below, traveling a distance of 12,800 kilometers, give or take 14 kilometers, that is the height. This is the diameter of the Earth. So the neutrinos which are detected from below would have traveled about 12,800 kilometers compared to 14 kilometers for those which are going down. And this is what we should expect if neutrinos are going through unharmed. It should be the same whichever way you are looking at it, whether down or up. But what you see in the data is very interesting. The downgoing neutrinos, all these neutrinos, the downgoing neutrinos are unaltered. In fact, you can see the data within errors very close to the expected flux. But if you look at the upgoing neutrinos, that means those which are coming from below us. So for example, if we are in India, this may be produced on the other side of the Earth in the Americas, and it is coming from below, traveling 12,800 kilometers, and the number of events is only half of that which is expected. So now there is a deficit here in the atmospheric neutrinos. But this deficit is, in the solar neutrino case, we saw that the deficit was slightly energy dependent, depending on the detected thresholds. Here it is direction dependent. If they are coming from above us, traveling 14 kilometers, they are unharmed, there is no deficit. But on the other hand, if they are coming from below, then there is a disappearance of these neutrinos, and you see the flux is only half of what should be expected. In fact, you can see more detailed results of these atmospheric neutrinos. They also measure separately nu E and nu mu type neutrinos. Or that means see, in the previous thing, there was no flavor distinction here. We put together all the neutrinos and just looked at their total flux, total number of events. Now we'll put a little more information and look at the electron type neutrinos and antineutrinos. The detector cannot distinguish between electron type neutrino and electron type antineutrino. It puts together all the events. So these two are the electron type neutrinos and these two are muon type neutrinos. Now let's look at the data for electron type neutrinos. The result is given as sub-GeV. That means all the events where the neutrino energy is less than 1 GeV, that means 1000 MeV. As I said, atmospheric neutrinos are 1000 times, or many hundred to thousands of times more energetic than solar neutrinos. So we use GeV instead of MeV as unit of energy here. Now they cannot distinguish this multi-GeV. After about 1 or 2 GeV, they cannot actually specifically say what the energy is, but they can say it is multi-GeV. So if you look at the electron type neutrinos, the expected is something like this red line, and what you observe are these black plus. These are the data and this is it. More or less, if you see this is cos theta, which shows the direction. Cos theta equal to 1 is the downgoing neutrino, which travels only 14 kilometers. And minus 1 is the one which comes through the diameter of the Earth. As you can see, there is a small difference, but it is not too much for sub-GeV neutrinos, electron type neutrinos. And similarly, if you go to multi-GeV neutrinos, there is almost no difference. Ignore this green curve, we will come back to it later. Now, if you look at this red line, which is the expected from the atmospheric neutrino flux data, and what is detected, there is more or less agreement. So in the electron type neutrino, there seems to be no big deficit. In fact, if the deficit is there, it is small, and it is also only for the upgoing neutrinos. But it is very dramatic in the muon type neutrinos. If you look at this, compare the red curve, which is what is expected, and the data points, these plus data points. So you can see that for the neutrinos which are coming from our above us, traveling 14 kilometers, there is no deficit. It agrees with the expectation. Whereas those which are coming from below, whether it is sub-GeV muon neutrinos or multi-GeV, that is high energy neutrinos, you always see a deficit. So there seems to be some distinction which is made between flavors. The electron type neutrinos, there is no deficit, and the muon type neutrinos, there is deficit. So therefore, the deficit is direction dependent, maximum for neutrinos traveling through the Earth and minimum for those coming from above. Now, what is interesting is you have to contrast the solar neutrino problem and the atmospheric neutrino problem. In the solar neutrino problem, we were looking at only electron type neutrinos at MeV range energies, and we saw the deficit. Whereas in the atmospheric neutrinos, we not only have electron type neutrinos, but we also have muon type neutrinos in the atmospheric neutrino flux. Not only particles, we also have their corresponding antiparticles. And if you put everything together, you see something that you are observing in these four data pictures, data points. Okay. So therefore, there is a puzzle. There is a solar neutrino puzzle which refers to electron type neutrinos, and an atmospheric neutrino puzzle which refers to the deficit of muon neutrinos. Now, the answers to both these puzzles, if we have to explain, then we will have to explain it through some property of the neutrino. If it was solar neutrino problem alone, and if this problem did not exist in atmospheric neutrino problem, we could have said that maybe we don't understand the sun very well. But no, we also have problem in other sources of neutrinos. When the source of neutrino is atmosphere also, we have a problem of the deficit. When the source of neutrino is sun, then we have a problem of deficit. And to this, there are also other results which came from reactor neutrino observation and other things. Now, putting everything together, it points to something very important, and that is we probably do not understand the neutrinos very well. They probably, the answer to these puzzles must lie in understanding some important property of the neutrino, that new property of the neutrino that we are missing up to now. And that is what we are going to talk tomorrow. So this is a primer on neutrino oscillations. In a nutshell, what I am going to tell you is that neutrinos may occur in one of the three flavors when they are detected: nu e, nu mu, and nu tau, depending on the detector's characteristics. And there are, of course, there are antiparticles, which we know they exist. In a nutshell, we are going to talk about a property called oscillations. What it does is to create a change in the flavor of the neutrino as it propagates in space. So if Ne is the number of neutrino flavors that is produced at the source, let us say sun, or in the atmosphere, then the detector probably sees only a small n, E number of neutrinos, because it can only see the electron neutrinos. Suppose the detector can only see the electron neutrinos. Because of this change of flavor, it sees a smaller number, because part of it may have appeared in the detector as some other flavor nu x, but the detector is not capable of detecting it. So even though the total number of neutrinos is the same, the detector is unable to account for certain type of neutrinos. It accounts only for some type of neutrinos that it is designed to detect. Now, what happens if there is a detector which is capable of detecting not only nu E from the sun, but also whatever has happened to the rest? So instead of the deficit, we should see the total. And in fact, this scenario provides for such a mechanism, and that in fact such an experiment was done, and in 2002 the Sudbury Neutrino Observatory finally detected all the neutrino types along with nu E's separately, and found that the total number agrees with the estimates provided by the standard solar model of Baca. So the problem or the controversies which began in 1859 were ultimately settled almost 150 years later in 2002 by the Sudbury Neutrino Observatory experiment. And MacDonald was the leader of that experiment, along with Kajita, who determined the atmosphere, who determined the properties of the neutrino through atmospheric neutrino puzzle. They got the Nobel Prize in 2015 for solving this age-old puzzle. We will talk about this solution tomorrow. There's not enough time today. So I will stop at this stage, and if you have any questions, we can discuss. Thank you.
Good evening, sir. Sir, we have certain questions on the comment box. Shall I read it to you, sir?
Let me see if I can get the chat. Is it in chat?
Yes, sir.
Okay. Somehow I am not getting the chat window. I don't know what to do.
Can you stop the presentation, sir? Then we will get one chart box.
Okay.
Chart.
Okay. I'll stop the share. Yeah, I got the chat
Yeah.
box. You can read it. Pooja, you can go ahead and read it.
Yes, sir. Mr. Akhil Krishnan has asked, how is it possible to predict remaining hydrogen in the sun using the neutrinos? So for that, Professor Vivek Datar has answered everyone.
Yeah.
The answer goes like this.
You can read it. Yeah.
Yeah. Natural fluorine has 75% and 25% chlorine 37, both being stable. Such a detector was proposed by Bruno in 1946 when he was at Chalk River Laboratories. We know how many proton-proton neutrinos are produced in the sun, and they match with the prediction of the standard solar model after accounting for neutrino oscillation, including the effect of the so-called matter effect. I don't remember the predicted lifetime of the sun, but the hydrogen should last approximately 10 billion years. So,
Yeah.
Professor Murthy, do you have anything to answer?
Yeah, in fact, the sun lifetime of the sun has been estimated more precisely. It's about 9.54 billion years, and at the moment it is around 4.5 billion years old. So what he says is correct. So we know the total mass of the sun, and we know the composition of hydrogen and helium. So all these things, there are other observations, heliosysmology and other observations, and the luminosity. So neutrinos is not the only one. And in fact, even before neutrinos were observed, we knew the composition of the sun from other experiment. But the neutrino flux calculations come from based on other observations, and therefore we have very good understanding of the sun through standard solar model. Yeah.
Yes, sir. The next question goes like this.
Can you increase your volume?
Yes, sir.
Ah.
The next question is from Miss Niharika. The question is, could you clarify on what threshold you're talking about in the detection of neutrinos?
Oh, these are threshold for the reactions that are actually used in the experiment. For example, if you are talking about Davis experiment, you remember it is nu E interacting with 37 chlorine going to 37 argon plus E minus. The threshold we are talking about is that this reaction can begin at about 0.81 MeV. Okay, so therefore the detector should be capable of detecting neutrinos above that threshold. This reaction does not happen if the neutrino energy is below the threshold. So the threshold means that the energy of the neutrino has to be above that value in order for that reaction to proceed. For neutrino electron scattering, it is nu E electron going to nu E plus electron. It's an elastic scattering. There is no threshold for it. It can happen because the same particles are there initially and finally. But we still talk about threshold in that experiment because in order to observe the knocked out electron in the final state, we observe it through its Cherenkov light. But the Cherenkov light is emitted only when the propagation of the electron.
Sir, you are muted your audio, sir. Can you check it out, sir? Murthy, sir. Your audio has been muted. Can you release your audio? Yes, sir. Now.
Is it okay now?
Now, sir. Okay.
Yes, sir.
Yeah, I don't know how it happened.
Okay.
Okay. So, yeah, sorry about that. So, how much did you miss?
You continue,
We
sir.
heard, sir. We
Okay, so the threshold for neutrino electron elastic scattering is actually the detector threshold. It's the observational threshold because electrons have to be relativistic and the electrons travel through water. Water is a medium. They can have relativistic propagation, or at least we can observe the Cherenkov light when their energy is above 5 MeV. So it is actually detector threshold, not the reaction threshold. So sorry, I should have clarified. There are two types of thresholds. One is the detection threshold and the other is observational threshold, which is a property of the detector. Yeah. What's the next question?
question goes like this. What happens if two different neutrinos interact with each other? So Professor Vivek Dattar has already answered for this. The answer being, since neutrinos interact weakly with matter and we do not have neutrino densities matching atomic number densities, two neutrino interactions are very unlikely except in supernova and such places where their densities are huge enough.
Yeah. Actually, this will be discussed by Professor Amol Dige when he talks about the supernova dynamics in more detail. So if you remember yesterday, he talked about the mantle, the neutrinosphere, and he said that there is a region in the core where neutrinos cannot escape. So the neutrinos cannot escape from that region because they are actually interacting with themselves. And they heat up the core through the neutrino interactions also. And there it is relevant. But otherwise, if you are talking about in the laboratory, observing neutrino interactions, that's extremely difficult. And they not only interact weakly, because unless they produce by subsequent interactions some charged particles, we cannot observe them. That is a very big problem with these neutrinos. Observing them is a very, very hard thing. One neutrino interacting with something is hard. Now you have two neutrinos interacting. It's double whammy there.
Yes, sir. That's the end of the question, sir.
Okay, thank you very much.
Can I make a small comment on?
Yeah, you are welcome.
Okay. The comment relates to this question of thresholds. So,
Yeah,
of course, the chlorine detector has a threshold of about 800 odd keV,
yeah.
but there are other detectors like Borexino. I might have missed it in maybe Murthy's lecture, uh, but they
Oh,
have
I
very
didn't.
low thresholds.
Yeah, I
And
didn't.
they can, in fact, measure PP neutrinos, which are the lowest energy neutrinos.
Yeah,
The PP neutrinos go all the way from zero energy to about 420 keV or something like that.
yeah,
And Borexino can detect them down to about 100 odd keV. So
yeah,
they have measured most of the PP neutrino spectrum.
yeah.
And that is, by the way, they are the most abundant neutrinos coming from the sun. They actually constitute about 90% of the total neutrino flux, or a little more than that, perhaps.
Okay.
So they have been detected by Borexino. Of course, Borexino has done various other very nice things, including some that I will talk about when I talk about the
Yeah,
PP and CNO chains.
yeah. No, I didn't mention Borexino because I thought you will.
Yeah,
Will you be covering it in your talk?
yeah, a little bit. Yes,
Okay,
that's right.
good. Yeah,
That's right.
because I didn't go into details of all experiments because
Yeah,
you will be doing it.
yeah.
Yeah. If you are not going to
The,
cover, then I can do it tomorrow.
Yeah. The other comment I want to make is regarding this proposal of Pontecorvo. The chlorine detector was actually first proposed by the theorist Bruno Pontecorvo. He's an Italian origin physicist. He was a contemporary of Enrico Fermi.
Funny.
And they worked together in Rome and so on. He, after his PhD, he moved to places including in the mid 40s, I think after the war, probably, or a little before the war, maybe, to Canada. And at the Atomic Energy Laboratories in Chalk River, he actually proposed this radiochemical detector to detect neutrinos. So the proposal was actually to detect neutrinos. So it was through solar neutrino, because at that time solar neutrinos were the most abundant source of neutrinos, and that's what he proposed. But this idea was actually taken forward by Davis when he did this experiment in a reactor, near a reactor.
Yeah.
But it so happens that that reaction goes through if it's a neutrino and not an antineutrino, and therefore he showed that reactors antineutrinos are different from neutrinos because this reaction didn't go through. And that's then later he with Bacall proposed that we build
Yeah.
a detector for solar neutrinos. And that happened then in the mid 60s onwards.
Pardon me, sir. There is one more question.
Yeah.
Uh, could you tell why there is a spectrum of energy in neutrinos? Is it because of their sources, or is it like anything to do with the distances?
No, it is not the distance. When we are talking about the energy spectrum, we are talking about the source. As I showed in the PP chain, which was the Bethe scheme of things, there are many interactions starting from fusion of two protons all the way up to production of slightly heavier nuclear beryllium and boron, and many of them decay. And some decays involve photons and some decays involve neutrinos. Now, normally what happens is, if it's a two-body decay, then the neutrinos come with very well-defined energy. This is simply a kinematic fact. But if it is three-body decay, then the neutrinos come out with continuous energy. So therefore, you will have both continuous energy neutrinos and in some specific reactions, line spectrum. It's called as a line spectrum and continuous spectrum. Both are possible depending on the reactions which I showed in the PP chain. Okay, so that that is what is used to calculate the neutrino fluxes and their spectrum from the sun. I think Professor Vivek Datar will say more about this.
Yes. Thank you, sir, for this informative session. It was a privilege to have you with us. Now, quickly moving on to the second session, we have with us Professor Vivek Datar. Professor Vivek Datar retired as the Director of INO project from TIFR in 2020. After passing out of the 18th batch of the BARC training school, he joined the Nuclear Physics Division with Dr. CVK Baba. He was awarded N.S. Satyamurthy Prize of Indian Physics Association in 1988. He was the head Nuclear Physics Division BAR from 2012 to 2015. In May 2017, he became the director of the INO project at TIFR. He was a postdoctoral research associate at the Institut de Physique Nucléaire at Orsay in France. His research work spans the fields of nuclear physics, particle physics, and nuclear astrophysics. I welcome you, sir, on behalf of the organizers. Over to you, sir.
Okay, thank you. Now let me share my screen. Maybe you should unshare the screen before I do that.
No, no, no. You can share now,
I can
sir.
share it. Okay.
Yeah,
Okay.
yeah.
Okay. Fine. Let me see. This is a PPT. So share screen. Uh, F5. I'm not able to. This is coming in the way. It's what control L. No, no, not here.
In downside, sir, here there is a. So yeah, that
Yeah,
not next, next, sir. Next two, next, next, next,
this
next,
one.
next, sir. Next,
Yeah,
next.
yeah,
Yeah,
okay, okay. Sorry,
yeah.
sorry.
Click, sir.
Yeah, yeah, yeah. Okay. Okay. So let me first of all thank the organizers and also Murthy for giving me this opportunity to talk to all of you. Um, uh, I am basically a nuclear physics guy who has dabbled a little bit on the periphery of nuclear physics and particle physics, uh, and do not really have a background of astrophysics. So this was an opportunity for me to learn a little bit about astrophysics. As somebody has said, the best way of learning a subject is to try to teach it. So I will give in the first lecture a non-specialist introduction to astrophysics, as I understand it, and of course a brief introduction to nuclear physics, because this was the brief that Murthy gave me. He said that it would be better probably to give a introduction to nuclear physics given the background of the audience. Uh, so let me go to the next slide. Yeah, so the lectures are like this. Uh, as I said, first one is on non-specialist view of astrophysics and introduction to nuclear physics. Then I go to the PP fusion reaction chains, as also the CNO chain, uh, and expand on a little bit on what Murthy has already told you, uh, but also discuss the experiments that are done and were done to measure nuclear reaction cross sections using low energy accelerators, and give you some examples. Hopefully, will give you a feel of what is involved in these experiments. And in the final lecture, I will say something about nucleosynthesis of elements beyond carbon, or up to iron, and then in next generation stars, or in collisions of neutron stars and so on, how production of still heavier elements occurs. Of course, this will be a little brief because I don't know too much about neutron stars collisions and the complicated calculations that go on there. Okay, so this is the brief outline of the lectures that I will be giving. And before I start, I should also probably give you some references, textbooks, and so on. Somehow there is this on top. I am getting something here. I don't know how to remove that, but in any case, okay. So the first line is a little not readable, but perhaps I have to live with that. Okay, so there are these. I mean, this is just a sample. There is an excellent book by Rawls and Rodney called by a very interesting title, "Cauldrons in the Cosmos." So, whoever it is that is brewing these various things in the cosmos, so that's the title. Very nice book. Rawls is a very well-known experimental nuclear astrophysicist. Then there is this relatively more recent book, Nuclear Physics of Stars by Iliadis. And the Introduction to Astrophysics is three Indians who have written it. It's accessible, this textbook. And of course, many of you might have read this, The First 3 Minutes by Steven Weinberg, A Modern View of the Origin of the Universe. It's a very readable, popular science book. And then, of course, there are many articles in well-known journals, review journals, Wikipedia, and so on. And also, just a sample of some of the observatory detector arrays is given for the square kilometer array, LIGO, and IceCube, and so on. Of course, there are much more. For the nuclear physics, I've given you some textbooks. Wong's textbook is a pretty decent one. It's fairly cheap. Of course, it is a bit old. It's about 30 years old. So, then there is a relatively more recent, of course, still it's 15 years old, Fundamentals in Nuclear Physics by a few authors from Europe. Basic Ideas in Nuclear Physics, 2004. And then there is an experimental, book that deals with experiments and techniques, how to approach, including, things like assembling a scintillator, photomultiplier, seeing pulses, and so on, doing timing measurements. So this is a book by Leo, Techniques for Nuclear and Particle Physics Experiments. Then in the nuclear physics domain, there are several places where you can get review articles. They're listed here, 1 to 3. But there is also a more sort of newspaperly, or you might say magazine approach, the Nuclear Physics News, which comes monthly, usually. But it's also, you can access this Nuclear Physics News at the website that is given, and you can freely download it. And it has also very nice articles written for not necessarily practitioners of the field, by people who are actually practicing. Okay, so with this, let me start with the introduction to astrophysics. Let's start with something to do with why it is called. What are we talking about? So, astronomy is, of course, a word derived from the Greek word, which means science that studies stars and the laws that go behind that. But it refers to actually study of everything in the universe outside the Earth. Astrophysics, of course, uses physics to study astronomical objects and phenomena. So that's astrophysics. So astrophysics actually has, uses almost all of the physics that exists, with the exception of very little, probably. But basically, all the concepts of physics find a place somewhere or the other in studying objects in the universe. Cosmology, of course, deals with the study of bigger things, bigger scheme of things, the origin and evolution of the universe as a whole. So you have cosmologists and you have astrophysicists, and so they talk to each other. And then there is a smaller subgroup which deals with one area of astrophysics that has to do with the nuclear processes that go on in stars, including the sun, and also maybe elsewhere in the very energetic places where explosions occur and so on. And that has to do with, because nuclear astrophysics studies the relevant nuclear processes, nuclear reactions, beta decays, photonuclear processes, and so forth. Okay, astronomy is probably the oldest of sciences because it is often linked with, it so happened that people who believed in astrology had to make observations of planets and so on. So there is this famous observatory in Jaipur, Jantar Mantar, sort of copy of which is there also in Delhi. Of course, humans made observations of the skies, and they must have made observations of many spectacular events because we have been around for about 1 million or more years. However, the recorded observations, the first one appears to be that attributed to the Chinese when they wrote something about observing the Crab Nebula. That was a supernova explosion which led to this nebula, and that occurred in about 1,000 years ago. Of course, astronomy really progressed significantly after the telescope was invented. And this was invented by Lippershey in 1608, that means about few hundred, 500 years ago, and improved upon by Galileo, who saw the moons of Jupiter, as you might recollect. Then by many people, Huygens, uh, Newton, who developed the reflector type of telescope, then Hadley, who made the first paraboloidal mirrors, which give a give a large focusing action and into a very small volume in space where you can observe them with the eyepiece and so on. And much later, people also discovered that you can coat these with aluminium, and then that is very good for the quality of the reflector to last for a long time. Uh, and at the end of it, the Hale telescope was built in 1948. It was the first really large telescope with a reflector of about 200-inch in diameter. That means about 15 odd meters. So uh, very recently, the Keck telescope has been taking excellent data at Hawaii on top of a mountain there, and it's about a 10-meter diameter one. It was built in 1993 to 96, but it's still working. And also, a couple of them are coming up, modern ones with adaptive optics to take care of the fact that the atmosphere, the fluctuations in the atmosphere ultimately cause worsening of the image of the star or whatever it is that you're observing far away. And to take care of that, you have to do tricks, and you have to tilt these mirrors depending on the observation of a laser beam which looks at a virtual star and so on. And that kind of adaptive optics is going into the 30-meter telescope at Hawaii, most likely Hawaii, but it's also possible because of local issues that it might go to some other place near Spain. And there is the European effort, which is somewhat bigger than this. It's a 39-meter telescope in Chile, on top of in a very high place in a cold desert. Okay, so I'm a little troubled by this. I somehow cannot see the top part of it. I find no way of getting around that. Okay, so how can we study the universe, and what are the probes that we have? The most obvious probe is the electromagnetic probe, electromagnetic radiation. And what is shown here is the atmospheric opacity. That means how much, it is opaque on a scale of 100% as a function of the wavelength of the electromagnetic radiation. So you can see that for very short wavelengths, which means high energies of the electromagnetic radiation, the quantum of radiation of a photon, that the atmosphere is actually opaque. It opens up at around something like about less than 10 micron, which is in the infrared region. And then it's again slowly rises back, and then, sorry, I give you a wrong number. It is about 10 nanometers or so. Okay, sorry, not 10. It's between 100 nanometers and 1 micrometer. So it's about maybe 300-400 nanometers. Okay. Then from 1 micron to about a little more than 10 micron, there are windows where the Earth is, the atmosphere is transparent, or more or less transparent to electromagnetic radiation. Then again, it goes up, it becomes opaque in a region from about, let's say, a few hundred micron to a few centimeters. Again, becomes transparent to a range between a few centimeters to about a few tens of meters, 15 meters or so. And this, of course, is the radio frequency region. So this is where radio telescopes come into action. Okay, and then it again becomes opaque at much higher wavelengths. Okay, so let me see. So to study the universe in this region, that means in the very short wavelength region, in the region of ultraviolet or X-ray region or gamma ray region, you have to actually put these things up. You can get away by putting it up at heights, but mostly you have to go into space. That means you have to put up these devices which look at the relevant electromagnetic radiation, the high energy electromagnetic radiation uh, in space on satellites. Okay. And there are now several of these working on satellites. Visible light, since it is observable, since the atmosphere is transparent, more or less, this is the visible region here shown, blue to red. We are fortunate that, or maybe that's how it developed, that humans have eyes that are sensitive to this. If they were probably, the atmosphere was transparent to some other wavelength and not this wavelength, we probably would have developed sensors which are in that region. Uh, Partly that reason. Okay, so uh, so that's how we can put telescopes on the ground and hope to observe them. Of course, there are also telescopes which are put up in space, which look at the visible and this region of the electromagnetic spectrum, because then you don't have the attenuation of the atmosphere at all. However, it is you cannot put up as big telescopes, at least with the present day technology, up in space as you can on the Earth because of logistics. Because every kilogram that you put out into on a satellite costs money. So if you make too big telescope, it's much more expensive to put it out into on a satellite. Okay, so infrared is of course absorbed, so necessarily you have to put up these objects in space. Radio telescopes, there's a huge window, and so of course there are many radio telescopes all over the world. I think this radio astronomy started in the 30s or 40s on a very small scale, but I think the Jodrell Bank in the UK, that really set the tone of things to come in the early 50s or late 40s maybe. And of course, now we have several of these operating. In fact, there is also already a beginning to that. The first, I think, set of radio telescopes in the square kilometer array has been put into action, and that was a news item a few days back. Okay, so this is now some general aspects on what is the angular resolution that you have. Again, the top part is blocked out. Can somebody tell me how to unblock this? Because there is that first 1.5 line is blocked because this mute and stop video, etc., is coming on top. Is there a way of going down?
A full screen, sir. There is options in the presentations. What happened? We are visible to all the text, whatever you were showing here.
Okay, but somehow I cannot see that. So what do I have?
But you have to scroll it, sir, I think. So it is from your PPT, so that we can't control it.
Oh, I see.
We can see, sir, whatever you were showing, it's clear to us.
Yeah, that's right. But I don't know how to remove, because I have to read it. I can't read what I have written myself.
We can't help you, sir, because it is from your side,
okay.
right?
So I'll do some guesswork. So the first line, I think, talks about the angular resolution that is possible with a probe.
Yeah, that is
of wavelength lambda, and that probe, let's say the telescope, you have an aperture whose diameter is of the order of a. Then the angular resolution at best you can get is of order lambda by a. Okay. So the human eye, for instance, which is a few millimeters, and we can only deal with the wavelengths which are visible wavelengths. That's about 5,000 angstrom units. Then the angular resolution of the eye is of the order of about 10 to the minus 2 degrees. Okay. The intensity threshold, by the way, is quite remarkable. I mean, one would have thought that the eye will be sensitive to maybe hundreds or millions of photons only, and nothing below that. But it turns out that the intensity threshold for maybe good eyes, and there is a Nature communication in 2016, is of order 1 photon. Just imagine, we are having detectors which are actually one single photon sensitive. It's fantastic, isn't it? Okay. The 30-meter telescope, on the other hand, has a much larger diameter and much larger aperture, and therefore, at visible wavelengths, it has a angular resolution which is about 4 orders of magnitude higher and that you can estimate, 4 millimeters to 30 meters. So that's of the order of 10 to the 4 times bigger in aperture. So no wonder it has a angular resolution of about 1,000 times, 10,000 times better. And that translates to about 3.5 milli arc second. Okay, the angular diameter, just to get things in a perspective, the angular diameter of the sun, and also it so happens the moon, because we see eclipses on the earth, is of the order of 0.53 degrees. Okay? You can, I'll come to some numbers in a later slide, so that you also can estimate things quickly. Back of the envelope calculation, I think one of which Murthy showed. Okay, now to image the black hole at the center of the Milky Way, which is, the diameter of the Milky Way is about 25,000 light years. That is 25,000 times the distance that light would travel in a year. Okay, uh, the mass of the that black hole is of the order of 4 billion times that of the sun, and so the so-called Schwarzschild radius of the black hole is about 12 million kilometers. Now, if you want to be able to see that, the aperture needed for a radio frequency, uh, even a high radio frequency, that means you won't do with 10 meter or 100-meter wavelength radio wave. You have to go down to millimeters scale wavelengths. So this comes in the gigahertz domain, or tens of gigahertz domain, uh, like the ones you use in your mobile phone and so on, which is a few gigahertz. So the aperture needed, if you were to use that kind of frequency to study this black hole, which is actually quite close if you consider it. The universe is so big, and just to see the black hole at the Milky Way, you would require an aperture of the order of 10 to the 4 kilometers. Okay? Now, of course, you can't make apertures of the order of 10 to the 4 kilometers. You can't have such a dish like that. So the experimentalists are very smart. What they do is they put smaller parts of that telescope at various places on the Earth, and then combine the signals that you see in each of these smaller telescopes, both in terms of intensity as well as in terms of phase. That's extremely important. The phase is extremely important in this whole thing, and so they have to be able to transmit the phase information without it getting distorted, and that takes a humongous amount of effort. But nowadays, with the capabilities that we have in communication, that can be done. And indeed, uh, just last year, the first image of the black hole in M87, which is a nearby galaxy, well, not so nearby, it's 55 million light years away, and but it's much more massive than that black hole is much more massive than the one in the Milky Way, more than 1,000 times as massive. Uh, that was imaged recently by a collaboration called the EHT collaboration. I forget now what this is. I forget what it stands for, but it's a collaboration basically to look at black holes and image them. Okay, so why were they able to image the a galaxy that was 55 million light years away, of course bigger, and not the one in the Milky Way? Well, that's because there is a lot of matter in between the center of our own galaxy and the Earth, and so it's they have looked at it, but it's taking them much more work to remove the background, or to peel off the background in order to get at the black hole in the Milky Way. They will probably do that in maybe a year or two. Okay. Now, again, I use the first line, but radio telescopes have been built, as I said, many places in the world. In fact, we have one radio telescope array at Khodad, which is maybe about 70, 80 kilometers from Pune. And this is doing really great work. I mean, most of the time, or a larger fraction of the time, it is used by outside users rather than Indian users. Uh, I think it had one nice event which occurred, I think, a month ago or something, where they detected an event which was extremely far away. Uh, Okay, and there is this upcoming square kilometer array, the first, I think, part of which got commissioned uh, and is already started taking data. But the square kilometer array refers to the total area of the aperture of many of these subunits, which are distributed in Australia and also in South Africa. So these two arrays in Australia and South Africa actually cater to somewhat different frequencies. Okay, so this is as far as the radio telescopes go. Uh, there are also other ways of looking at or other regions of the electromagnetic spectrum that are accessed. And one of them is the so-called ultra high energy gamma rays to study very violent processes that are going on in deep parts of the universe. Uh, and they actually make use of the atmosphere surrounding the Earth as a detector material. So these ultra high gamma rays that come basically straight, except for maybe some small refractive effects, which are very tiny. Uh, they come basically straight from the source, unless there is something which blocks them, maybe in the way of a star or a galaxy. But these things are so relatively so sparse that you hope that that doesn't happen too often. So you can observe these events when the ultra high energy gamma rays actually cause a electromagnetic shower in the upper parts of the atmosphere. Now, when they do that, they produce energetic electrons and positrons, and since they are moving at speeds that are higher than the speed of light in that medium, of course, the refractive index of air is not very different from 1. It is 1.00 whatever 1 or of that order. It's only a million, sorry, a fraction of a thousand fraction different from 1. Nevertheless, these are highly relativistic electrons and positrons, so they produce this Cherenkov radiation. And then that Cherenkov radiation, Cherenkov photons, move down and get detected by collectors of this light. And they can be big as, in fact, the dishes can be as big as the ones which you have in normal visible telescopes, reflected kind of telescopes. Uh, Again, these are built by making many of them, distributing them over area. So you look at the shower pattern, the light that you see in each one of them, and then you can point back the direction of the source from where it is coming. Okay. There are, as I said, also space-borne telescopes, and Hubble is the one which is most famous. You must have, I'm sure, seen beautiful pictures from the Hubble telescope. And it is already, I think, about 25, 30 years old, is still taking data. But at some stage, I think it will run out of, there'll be problems cropping up. And the technology has certainly changed. So there is the upcoming James Webb Space Telescope, which will be put up in the next few years, probably in the space shuttle or maybe in another dedicated space vehicle. Okay, what are the other probes of processes that are going on in the universe? As Murthy and also Amol mentioned, cosmic rays are, of course, they do tell us about what is going on in the universe. Of course, the cosmic rays have charged and uncharged particles. The charged particles, which are mainly protons, and also helium-4 in small numbers, and then even heavier nuclei. They have the problem that if they are coming from extremely energetic sources very far away, then they are affected by the magnetic field. They can be affected by magnetic field from intergalactic magnetic field, by stars. Neutron stars, for instance, have very high magnetic fields around them. Even the Earth has a magnetic field, not very large, but good enough to bend low energy particles. So it is the most energetic particles that are bent the least, but even then they would still undergo bending. So you, by looking at these particles, you may not necessarily be able to point back to the source. Although for the most energetic ones, there is a likelihood that you do so. And there are huge arrays which are now looking at these cosmic rays, charged particles, and the secondary particles that are produced when these charged particles interact with the upper atmosphere and so on. So one such example is the Pierre Auger Observatory, which is on the ground in South America. It's, I think, in Argentina. Uh, Again, in a desert-like region, which is far away from civilization, because of course they don't want to be cluttered up with things that come from man-made sources. But there is also this remarkable detector, particle detector, which is put up in space. And this was actually a pet project of a Nobel laureate called Sam Ting. And he put up this magnetic spectrometer, which very accurately measures charged particles through spectrometry, just as is done in high energy particle physics experiments. And this is aboard the International Space Station. Uh, okay. And of course, as part of cosmic rays, we also have neutrinos. So neutrinos from the sun have been observed by Super Kamiokande, but much more energetic neutrinos have been observed by the so-called ice cube detector, which is 1 kilometer cubed uh, ice detector. So it operates on the same principle as water Cherenkov detectors. When particles which are produced as a result of neutrino interactions, charged particles, move with a speed greater than that of light in that medium, then they produce Cherenkov radiation. And photomultipliers are strung on string, are mounted on strings which go down vertically uh, below about 1 kilometer of ice down to about 2.5 kilometers or so of ice. And they observe this, sorry, 1.5 kilometer to 2.5 kilometers, something like that. And they observe this extremely high energy interact neutrinos. Why extremely high in the beginning? Because they wanted to study very violent processes in the universe, and the neutrino doesn't interact very much. So you expect the neutrino to directly point back to the source uh, and not be disturbed by the intervening matter. That's number one. But since they are so very small in number, the flux is extremely tiny. You cannot do with even the biggest detector at that time, which was Super Kamiokande, and hope to get any events. So they thought of this ice cube detector, which is a kilometer cube device under the South Pole. And there they have observed extremely energetic, of the order of 10 to 15 TeV events, and many more of TeV energies and so on. And this is progressing. They are now populating more photomultipliers there, so as to even go down in threshold to of the order of about 10 CeV or so in a smaller volume. Okay, so this is as far as cosmic ray goes. Then, of course, there is another observational tool that we have, and that has come up in the last few years, and that is the gravitational waves. This has been a great development because gravitational waves were predicted about more than 100 years ago in 1916 or so, and were detected 100 years later in an experiment that is just mind-boggling in terms of the technology that was required. And these were observed for the first time in a black hole merger. And now, of course, several have been seen, including a neutron star merger. Uh, the sensitivities of these detectors is going up. The number of these detectors is going up. In fact, there is one coming up in India as well, a place called Hingoli. It's expected to come up in 5 6 years from now, maybe less if they go work hard at it and get all the support and so on. Uh, the idea is that you can triangulate using timing. So you can get the direction of the source much better if you have something which is diametrically opposite to the detector in the US. So the two detectors in the US are about 3,000 kilometers apart. But if you have a detector in India, that is almost 13,000 kilometers apart. And together with detectors in Italy, which is already up and coming, but also a detector in Japan, we will be able to point back to the source of these violent events, black hole mergers, or black hole star mergers, or black hole maybe, or neutron star mergers, and so on, much better within, I think, a couple of degrees or something. There is also R&D based on space-based laser interferometers like the LISA project. So LIGO is, of course, based, it's a Michelson interferometer using lasers, and of course, uh, humongous improvement on the Michelson interferometer in terms of technology and so on. But the limitation is basically the distance right now that we have between the two farthermost gravitational wave detectors. So if you go into space, you have that as an advantage, but there are also other advantages and so on. So that project is going on, and probably it will come up in 10 to 15 years from now. Okay, so this is a nice picture of the GMRT, the Giant Meter Radio Telescope. I don't remember the exact number, but there are about 25, 30 of these huge dishes separated. Put up over an area of something like 25, 30 square kilometers, or more than that, perhaps. I don't have that number right on top of my head. It looks beautiful when it's lighted up. And this is a picture of the LIGO gravitational wave detector at Hanford. So the Michelson interferometer was basically a tabletop device that in order to detect gravitational waves, you have to make a device which has arm lengths not just of a few meters, but a few kilometers. So in this case, it is 4 kilometers. And you also have to shoot the laser back and forth about 1,000 times, so as to effectively increase it by 1,000-fold. And that's how you get an effective arm length of about 4,000 kilometers. So you basically amplify the small amount of distortion that you have in the mirror 1,000-fold. And that's how you can actually measure small strains of the order of 1,000th of a nuclear damage. Okay, so this is a fantastic achievement, and this has really come up in a very big way. And let me just also point out a difference between the gravitational wave detectors and the other kinds of detectors. The other kinds of detectors have this, 1 by r squared dependence. If there is a source, you have a 1 by r dependence. Here, you're measuring a strain. So you're actually getting a measure of the amplitude. And that goes like, therefore, 1 by r rather than 1 by r squared. So gravitational, apart from the fact, of course, that gravitational waves are even more weakly interacting, much, much, much more weakly interacting than the neutrino. So, of course, they don't have any attenuation at all. The universe is transparent to gravitational waves, except, of course, if they have to come out from something going on in the black hole inside a Schwarzschild radius, that we can't tell, of course. But apart from that, gravitational waves can go everywhere. And it's only that it's very difficult to detect them because they have the gravitational, the interaction constant, the fundamental interaction strength is about something like 40 orders of magnitude smaller than the strong interaction strength. Okay, so I want to emphasize that's how the LIGO will go much further out than any of the other detectors like cosmic ray detectors or neutrino detectors or other electromagnetic detectors. Okay, now I don't see again the title of this what I'm seeing, but I just will give you some background as to the astrophysics of the universe to put the things in perspective. I'm going perhaps a little slow, but I think I will stop at the time that the organizers tell me to stop, and then we will continue from there in the next lecture. As I said, this is the first time I'm saying something about astrophysics, so maybe I'm getting carried away by some of these things, but I hope you will excuse me for that. And the other thing I would like to ask is if you have any questions, and if I can answer them, I will certainly do so. So please don't hesitate to ask any questions. Okay, so the sun, which is our closest star, is the kind of run-of-the-mill star in the scheme of things in the universe. It is also not at the center of things, which is, of course, fortunate. It is on the edge of the Milky Way, where the density of stars is not too much. So you don't have the possibility of a supernova occurring that often. close to you. The Milky Way itself is a part of a cluster of galaxies, of which there are many in the universe. There is an overall expansion of the universe, which was discovered by Hubble in 1929, where he found that stars are moving further and further away from each other. Okay, and the further away the star is, in fact, it is moving away faster. So there is a relation, V equal to Hubble constant. At that time he called it some other constant, but now it is known as the Hubble constant. The velocity at which the star is receding, on the average, of course, because they have their local motions around, let's say, another star, if it is a binary system, or the center of the galaxy and so on. But this is the average motion of the star. That is roughly proportional to the distance at which it is, and so this goes by this relation that the recession velocity is proportional to the distance at which it is, and this holds for any observer in the universe. Okay, any observer is as good as any other, and so actually it is space which is expanding. Okay, this is a somewhat maybe difficult concept that. But the analogy which you can give is, suppose I have a rubber sheet and I stretch this rubber sheet, then that is in 2 dimensions, whereas the spatial dimensions of the universe are 3, and in 3 dimensions it is actually expanding. Okay? So this was some discovery that was extremely important, and we'll come to some of the theories of to explain that so-called Big Bang a little later, the consequences of that. Now, okay, so this is already here. How do you get this overall expansion? If the universe is expanding now, it must have been expanding right in the beginning, but at some point it must have been more compact, and perhaps it was a singularity at some point, and from there it expanded, and then kept on expanding. Now, whether it will keep on expanding forever or not, that is an open question, I guess. But certainly, at some point, the electromagnetic radiation fell out of equilibrium with the other material, matter, and that happened, we think, I'll come to that in a later slide, about 400,000 years ago. No, sorry, at the life, when the universe was about 400,000 years old. And at that point, then the black body spectrum started cooling because this universe started expanding. So if the length scale, so lambdas expanded, and you got to a point at the present time where this black body spectrum shows characteristics of a black body of temperature about 3 degree Kelvin, and this is the so-called cosmic microwave background radiation. Okay, so just to put the scheme of things, this is a picture taken from Wikipedia source. So we are here in the solar system. I hope you can see my pointer. So I think if I right click, I'm supposed to get a laser pointer. Let me see if I can do that. Pointer options, laser pointer. Okay, okay, here. So this is the sun. This is Jupiter. This is Saturn. We are on Earth, which is a nice blue planet, which is very forgiving of many of the bad things that we do, like pollution and so on. But it's a very nice place to stay in the universe, very friendly to life. And then this solar system is actually part of the Milky Way galaxy. So that is what is shown here. The Milky Way itself is part of a local group of galaxies. I think that's about 30 or so in number. And that in turn is part of a so-called local supercluster of galaxies, which is part of the universe. So there is a sort of large-scale structure to the universe, but it roughly looks uniform in all directions if you average out over these objects like galaxies, stars, galaxies, and so on. Okay, now for some numbers. I thought it would be a good idea. Okay, let me ask the organizers. This is about 6:15 now. I have up to what time? Hello?
You have up to 7 o'clock.
Okay, okay. So that's still 45 minutes. Okay,
I'll
fine.
give you about 5
Up
minutes.
to 7 o'clock, sir.
Yeah, okay. So, but by the way, nobody is asking questions. I don't know. I when I do it full screen, I can't see the chat box. If there are any questions, maybe the organizer can just stop me and ask that question.
Yes, sir. There's a question
Yeah, please.
from Mr. Akil Krishnan.
Yeah.
The question is, what are microwave detectors? How
Yeah.
how can we find the earlier state of cosmic using microwave radiation?
Okay. So, microwave radiation, I mean, you have the same kind of sensors that are used in your mobile phone and also in some of these telescopes. Basically, they will give you a voltage, and these can be solid state devices, gallium arsenide or such devices, which can produce a small voltage. And of course, these devices have to be extremely fast. If they are in the gigahertz or higher frequencies, they have to be extremely fast. Of course, at lower frequencies, you can have even you can have so-called resonant circuits that can pick up this radiation in a certain frequency band, a narrow frequency band, and you can have many of these tuned to different frequencies. So you can collect these and then mix them later, or you can analyze them separately. But in the microwave region, of course, you have these tiny solid-state devices. In fact, the first one of which was made by our own J.C. Bose, for which he even has a patent. I think he produced and detected something like 60 gigahertz frequency radiation. Okay. I don't know whether that answers your question, but I'm not an expert in these devices, but I certainly know that this is how it is detected. Okay.
So that's all for now, sir.
Okay.
Later, if any other questions are there,
Sure.
we'll communicate with
Please
you.
feel free to interrupt me. Okay. Yeah.
Yes, sir.
Okay, so now coming to the some numbers, just to put a perspective on the distance scales and angular scales and so on. The sun is about zero point 0.7 million kilometers in diameter. If you remember, the Earth is about has a diameter. The radius of the sun. So the diameter of the sun is 1.4 million kilometers. The radius of the Earth is about 13,500. The diameter of the Earth is about 13,500 kilometers. So there is a difference in by about a factor of 100. So the Earth is 100 times smaller than the sun in diameter. Uh, the sun weighs about 2 10 to the 30 kilograms, and its luminosity is about 4 times 10 to the 26 watts. Okay, so this is you can see the luminosity that Murthy gave is the same number. In astronomy and in astrophysics, they talk about there is also some amount of jargon. Uh, they use this unit of astronomical unit. So that one astronomical unit is the mean Earth-Sun distance. So that's about 1.5 10 to the 8 kilometers. So 150 million kilometers. 1 parsec is the distance associated with the uh, you know distance of one astronomical unit which subtends 1 arc second of angle. Okay, so if you have an object of dimension 1 astronomical unit, which is this 1.5 10 to the 8 kilometers, and you are at some place where it subtends an angle of 1 arc of a second. Okay, so 60 seconds make up a minute, 60 minutes make up a degree, and of course 57 point something degrees makes up a radian. Then that distance turns out to be 3.3 light years. Okay. So 1 parsec is about 3.3 light years, which is roughly about 3 into 10 to the 13 kilometers. Okay. You can 1 year is about 3.1 10 to the 7 seconds. Light travels at the speed of 300,000 kilometers a second, and you can work this out. I told you about this Hubble constant, that the universe is expanding at a certain rate, and that rate at which it is expanding, which is determined by this Hubble constant, we have now measured it to much better accuracy than Hubble did, because Hubble had a much smaller sample, because the telescopes in those days were much smaller in diameter, and also, the ways of analysis and the statistics has gone up and so on. So now we know that the Hubble constant is about, I believe it is about a factor of 2 different from what Hubble had found it to be, and it's about 70 kilometers per second per megaparsec. So megaparsecs is 10 to the 6 parsecs. Okay, the radius of the Milky Way I already told you is about 25,000 light years. I hope I'm correct. I hope I didn't get it wrong, but sort of diameter, I put it as radius, but I'll check it. I think it is, hopefully it is correct. The number of stars in the Milky Way is about 100 billion, 10 to the power of 11. And the mass of this galaxy is 10 to the power of 12 times the mass of the sun. Okay? So a typical star is actually 10 times more massive than the mass of than the sun. Okay? 10 times more massive than the sun. So the sun is actually a very puny guy as compared to the average star in our own galaxy. Leave alone other galaxies where you have much bigger stars and also much bigger black holes at the center and so on. As I said, we are part of a local cluster of galaxies where there are about 30 galaxies within a megaparsec distance. The nearest galaxy cluster is the Virgo cluster, which is about 14 megaparsecs away, and that has about 1,000 galaxies as opposed to only 30 in our local cluster. That cluster, the Virgo cluster, has this M87, the black hole in which was just imaged very recently, and that of course made a splash all over in all newspapers and magazines and so on. Then, as I said, there is a cluster of clusters called a supercluster on the scale of 30 to 300 megaparsecs. And perhaps if we go out even further, maybe there will be, the super squared clusters or whatever, which we might do once we have better telescopes and which reach out further in space, as also the gravitational wave detectors and so on. Okay, these are some constants which might be of some interest when if you want to do back of the envelope calculations. For instance, this Boltzmann constant is about of the order of 100 microelectron volt per Kelvin. So if you take 3 Kelvin, this is about 0.25 of a millielectron volt. If you take 300 Kelvin, that's about 25 millielectron volts. H cross is this number. Then this is the Stefan Boltzmann constant. So in fact, using this constant and the luminosity, you can work out what is the surface temperature of the sun. This is a back of the envelope calculation. It will turn out to be a few thousand degrees Kelvin. E squared, if you want to do some nuclear physics estimates as to the Coulomb barriers and so on, this is a useful number to have. The charge squared is in units of MeV Fermi is 1.44 or so. The lifetime of the neutron, of a free neutron, by the way, is 880 seconds or so. There are, of course, some controversies going on as to is it like this or is it a few percent different, 1 or 2% different, but it's of this order. This is important when you talk about the early universe, because these free neutrons can decay. Of course, once they get bound in nuclei, then the energetics of those nuclei decides whether or not that nucleus will decay. Okay. Then, just to give you a scale of things, the lifetime of the beryllium-8 ground state is of the order of 10 to the minus 16 seconds. So it's much shorter than this, but it's much longer than the time light takes to travel across the nuclear dimension. The nuclear dimension of the order of a Fermi, and that's 10 to the minus 13 or so centimeters. Light travels at 10 to the 10 centimeters. So the typical time scales are of the order of 10 to the minus 22 or 10 to the minus 23 of a second. So the lifetime of the beryllium-8 nucleus, which actually undergoes decay through the strong interaction. It decays into 2 alpha particles, which are strongly interacting particles. Of course, they have the Coulomb interaction, but what determines the lifetime is, of course, a combination of both, because the Coulomb barrier decides it makes it slower, and that's why it becomes typically 6 to 7 order of magnitude smaller than typical time scales of strong interactions. Okay, now a little bit of again how these stars form. So at some point in the evolution of the universe, you had gas clouds, and then they came together to form stars, and the gravitational energy, basically potential energy, got converted to heat, and then if the star was large enough, then or the mass that accumulated was large enough, it would actually form a star. Otherwise, it could be, for instance, a Jupiter-like planet forever. Uh, Not necessarily with the same composition, but composition of hydrogen and so on, hydrogen, helium, and so on. Okay, so if it is in the range of less than about 8 times the solar mass, then you have things happening which happen in, for instance, our own sun. But if it gets heavier, 8 to 20 times solar mass, then you can eventually, at the end of the lifetime of this star, you can get a supernova explosion with its consequences, like emission of heavy nuclei which are formed there, formation of a neutron star. Or if it is greater than about 20 times the solar mass to start with, then you can, in these explosions, you can even end up with a black hole. These supernova are also sites for rapid neutron capture, because in supernova, as you saw in the talk by Amol, you have electrons combining with protons to form a neutron. Okay? And so there's a large number of neutrons that are there, and they can interact with the iron core, and they can lead to elements beyond iron. The neutron is, as you know, a neutral particle, so it doesn't have the same, uh, difficulty in entering a nucleus as a charged particle would have. A proton, of course, faces a Coulomb barrier when it tries to enter a nucleus. For instance, the iron nucleus would have a Coulomb barrier of a few MeV, and so unless it has that kind of energy, it won't be able to interact with the iron on a nuclear scale. But a neutron has no charge, and it can merrily get into the nucleus. Uh, Okay, so this is one of the ways in which heavy elements can be made, as we will discuss in a little more detail later on. And that's where the heavy elements are made. And then, of course, in an explosion, they are dispersed into the cosmos and to be accumulated by next generation of stars, because this ultimately finds its way in gas clouds, and then they come together. And so the sun is believed to be a second or even a third generation star, not a first generation star, because it already has heavy elements. Uh, the the neutron star merges also can take place, and in fact, they are touted as of now to be the candidates to, if you want to fully understand the abundance that we have of the heaviest elements. Uh, what the experts say is that the rapid neutron capture in supernova explosions is not really quite enough to produce the abundances of these heavy elements. And neutron star mergers are probably needed if you want to account for the abundances. For the heaviest stars, even if you were to form a neutron star, then the neutron degeneracy pressure is not enough. Okay, and so because neutrons are fermions, so when you compress them, they don't like to sit together. But if the star is heavy enough, then of course even that degeneracy pressure cannot hold it back, and then ultimately it leads to a further contraction and then to a black hole. And then, of course, a black hole is characterized, among other things, by a Schwarzschild radius, out of which nothing is expected to get out. Uh, okay. Of course, you can have a black hole which is not just zero angular momentum, but it can be a spinning black hole. And then they have the so-called accretion disks, where matter falls in and is rotating also. And you can also have magnetic fields. And these are probably the sites of the so-called blazars, which lead to the most energetic cosmic rays, and perhaps also to the most energetic neutrinos. Okay, I said that the photons which decouple at about the life of the, when the universe was about 380,000 years old, then uh, the universe kept expanding, and uh, we now have measurements of the so-called black body spectrum of the universe, which is the cosmic microwave background spectrum, which is there in all directions. There are very small, tiny asymmetries associated with this, but if you account for those because of local motions and so on, then the this background radiation that you see is really a spectacularly good black body spectrum. And you can see the error bar on this. This is 1 part in about 2700. Okay. The data points that are there on this curve are much smaller than the thickness of this line. So it's a really fantastic black body spectrum, 2.7 degree Kelvin. This is again taken from this source. And this was, by the way, discovered in the early 60s when, as a result of some prodding by Dickey and Gamow, some 2 scientists in Bell Labs decided to look for it. And initially they believed that this was coming from some noise in their detectors, but finally they talked to the right people, including Dickey and Gamow, and then they were convinced that this is the microwave background radiation that pervades the whole universe. And then, of course, this was a very nice signature that they found of the so-called Big Bang, something that the universe blew up from a very tiny or maybe even a point-like object to the present day universe. And this is one of the evidences of such a event which took place some 13, 14 billion years ago. And Fred Hoyle, who was a proponent of the so-called steady state universe, which doesn't believe that there was such an event that occurred, he disparagingly called it the Big Bang. Okay? But that name stuck, and we still call it the Big Bang. So the initial singularity, which could very well have been a kind of quantum fluctuation, because the total energy of the universe, if you add up the potential and energies in the mass and so on, it actually adds up to close to 0. So, I mean, this is at least one school of thought. This could be just a quantum fluctuation. We don't know really how that occurred, but we believe that this grew rapidly, and there is a theory for this called inflation. This is not at all clear how this happens, because it expands much more rapidly than you would expect from the limiting velocity of light. But the whole fabric expands extremely rapidly. And then energy density fluctuations there in this inflation process lead to clumps of matter that condense later into stars, galaxies, and perhaps even the small asymmetries that or anisotropies that you see in the microwave background radiation. But that's at the level of a few or tens in million. Okay. Okay. So initially, only elementary particles and antiparticles existed, like quark, antiquark, the gluons, leptons, photons, W bosons, and so on, and maybe something else if we discover heavier and heavier particles. But then when it cooled down, these quarks and gluons combined to form nucleons, which mean neutron and protons. So that happened when the temperatures decreased to about 100 MeV or so, which is what happened in a few seconds. Then in a few minutes, nuclei were formed. And it can't be much larger than a few minutes, because otherwise the neutrons would have decayed, and then you won't form nuclei. Then you will only have protons and electrons. And then the richness that we see because of all these nuclei would not be there. So this had to happen on the scale of a few minutes, when the temperatures were of the order of 5 MeV. And much later, you got atoms. That means it cooled enough that the electrons and nuclei combined to form atoms, and they were not disrupted by the high temperatures then prevailing. And later, 380,000 years, down to such a level that the background radiation also could not disrupt atoms. So when the temperature came to about 10 electron volts, that's when electromagnetic radiation is supposed to decouple or not really break up atoms. Okay. So that's what is meant by this jargon called decoupling. And from then on, the universe has expanded, and the black body radiation has gone from that corresponding to 10 electron volts to the present uh, temperature of 2.7 Kelvin. And we now guess from various pieces of evidence that the present day age of the universe is about 14 billion years. So this is a picture taken from a poster that we had made for Vigyan Samagam, which was uh, there in 2019 to 2020 and traveled in the 4 metro cities, showcasing the uh, 6 or 7 mega science projects that India is involved in. It included, of course, homegrown projects like the India-based Neutrino Observatory, but also LIGO India and other projects where India is participating in a major way, like the 30-meter telescope, the ITER project even. It's not really an astronomy project, but an effort to recreate something like what happens in the core of the sun in a slightly different way, the fusion of deuterium and tritium, two heavier isotopes of hydrogen. And then the FAIR project, which is the anti-proton project, an ion research project in Germany. CERN, of course, we have been collaborating for many years. And one more project here, which is the Square Kilometer Array, which builds on our capabilities in the GMRT. Okay, so this shows the development of the universe right from the Big Bang to very short time scales where you have a quark gluon soup, which is being investigated, for instance, in places like RIC and the LHC, and then the formation of the first stars, which will be investigated by the Square Kilometer Array, then 500 million years ago, which will be investigated by the 30-meter telescope. At the age of a billion years, things like stars form and reaction take place. So this is akin to that, not quite that, as I said before. And then, of course, the TMT will also look at extraterrestrial objects where you could even have life and so on. So this is the time scale. So this is where we are right now at about 14 billion years from the Big Bang. Okay, so this is just a recap of that. The first picosecond or so, we have the so-called Planck epoch. Before that, we have the Planck epoch, where all these interactions merge together and probably have a single interaction. Then there is rapid inflation. Space expands extremely rapidly, but it also includes quantum fluctuations. That's what gives rise ultimately to stars and galaxies. Then at a microsecond, you have a quark gluon soup which forms. At a second, you have neutrinos which decouple and lead to the cosmic neutrino background. So actually, the neutrinos decouple much earlier than the photons. They have actually a lower temperature. They have been expanding since then. Quarks coalesce to form nucleons, as I already said, to neutrons and protons. And then at 2 minutes or so, the conditions are right for primordial nucleosynthesis. That means nucleosynthesis that occurred in the very beginning stages of the universe expansion. And you got things like only the light elements are formed, and we'll come to that later. Light elements like deuterium and helium and even lithium. At about 20 minutes or so, when the universe is 20 minutes old, fusion stops, but the hot plasma just cannot sustain atoms, because even if atoms are formed momentarily, they would get broken up by the energetic particles that are around, including photons. At 50,000 years, now photons which were dominating the universe, the then universe, now matter starts dominating. So the energy in matter now becomes significant. So at 100 kilo years, the first molecules form. In fact, this is a molecule that has been first observed in 2019 because of its the way you observe it is through terahertz radiation, for which the technology is just developing. And it's a helium H plus molecule. I mean, you have a helium nucleus, a hydrogen nucleus, and 2 electrons surrounding that. So it's basically like a hydrogen molecule, a neutral hydrogen molecule, where you replace one of the hydrogens by a helium. So it becomes a positive molecular ion of helium H plus. Um, this tells you about what is happening at the level of 100 kiloyears. At about, as I said, 400,000 years, neutral atoms form, and the universe now becomes transparent to photons. So you call them as decoupling from the atoms. So initially, the universe was pale orange in color. Then, as it expanded, wavelengths increased, and of course, now you have this color, which is in the visible range, becoming so large that it now becomes microwave radiation. So from a few thousand angstroms, it becomes now the order of millimeters. Okay, at the level of about 1 billion years, the thermal radiation becomes dark because it has gone now into infrared. We can't see it, and the universe keeps on expanding. The earliest stars are formed. You have reionization using high energy gamma rays from stars, dwarf galaxies, and so on. So they produce energetic particles which can again ionize atoms. So this is in this time scale. And of course, 1 gigayear to the present time, the universe is roughly like what it was today. Of course, there were a different set of stars than now, but roughly speaking, it was the same. Now, we don't know, of course, whether this expansion of the universe will continue forever, or will it come to a halt at some time and then again start contracting, leading to a inverse of the Big Bang, things coming together and forming a very dense, maybe even a singularity. We don't know what happened. One of the things that I would like to point out is that what we see in the universe is only matter and not antimatter. And from all the fundamental theories that we knew about, we would have expected equal amounts of matter and antimatter. So Sakharov in '67 put down the conditions. I think there were 3 or 4 conditions that he put down, which included, of course, violation of baryon number, lepton number, and so on. You know, non-equilibrium conditions. But one of the key conditions was that CP should be violated. That means matter antimatter asymmetry has to be there. So consider if you have 10 to the 10, let's say, particles produced and roughly 10 to the 10 antiparticles produced, just differing by 1 number. Okay, so maybe 9 nines, so many antiparticles and 10 billion particles being produced. Now these 9999 whatever 9 particles would all combine with their corresponding particles and produce radiation, but one fellow would be left out, and that is supposed to have happened in the early universe. So how can that happen? There have to be something beyond our present understanding of the theories that we have, and there has to be something called CP violation, which means matter antimatter asymmetry has to be there. Now we do know experimentally of matter antimatter asymmetry in interactions, in particle high energy particle interactions, in the kaon system, in the B bar, B0 bar system, K0 bar system. But it turns out that that is not enough to explain the asymmetry that we see in the universe. So it is there, but it's too small. And so perhaps the neutrino, which has produced so many surprises, might give us the answer to this question as to what are the processes that contribute to this asymmetry. Because they certainly have to be there if we have to understand the predominance of matter in the present day universe. So this is one of probably the 10 fundamental questions that scientists would like to have answers to. And so especially in the context of neutrinos, because we already have some smoking gun signal that CP is violated, and quite to a large extent if the experiments are shown to be correct. Of course, as happens in science, you get the first indication, but sometimes these indications may turn out to be wrong. Better experiments have to be done, and they might go in the same direction, or they might go in opposite directions. So this is up to better experiments to confirm or disprove what has been observed. Okay, so let me come to Big Bang nucleosynthesis. So I told you that once the nucleons are formed and the temperatures have cooled, such as not to break up the nucleon into its constituent quarks in a kind of quark-gluon soup, once that quark-gluon soup has cooled down at the level of about 100 MeV or so, then you form hadrons, including nucleons. So, okay, I should have probably put a slide on what are the quarks that make up these nucleons. So let me just say it in words. A neutron is composed of the UDD quarks at the valence level. Of course, there might be other quark-antiquark pairs produced virtually, and of course, gluons inside the nucleon itself. But at the valence level, so at the barest level, it contains the up quark and two down quarks. And up quarks have a charge of plus 2/3, a fractional charge. You might say, have you observed fractional charges in nature? No, we haven't. But the theory of quantum chromodynamics tells us that the forces between quarks increase as a function of distance, not decrease like in electromagnetic or gravitational interactions, or even in weak interactions. They actually increase. And so we cannot pull two quarks apart. And therefore, we have no way of taking a quark apart and measuring its charge to be 2/3. We can do that only indirectly. And indeed, indirect experiments have told us that these fractional charges exist in the midst of a nucleon. Okay, so N consists of a UDD combination plus other gluons and quark-antiquark pairs virtually. A proton consists of two U quarks, so 2 plus 2/3 quarks, and 1 minus 1/3 quark. So it has a positive charge. And of course, their antiparticles have the reverse. So the antineutron would have a U bar, D bar, D bar, and the antiproton would have a U bar, U bar, D bar. Now, in the Big Bang nucleosynthesis, the reactions that are relevant are, as I told you, the fact that the neutron decays. So if these reactions that produce heavier things don't happen, then the neutron will have decayed into a proton, electron, and an antineutrino, electron type of antineutrino. But a neutron, of course, can combine with a proton because, as I said, you have neutrons and protons in this soup of hadrons. So it can combine through electromagnetic interaction. This is called radiative capture. So you can produce a heavy counterpart of the hydrogen nucleus, which is a combination of neutron and proton, deuterium, and a photon. A deuterium can combine with a proton to give you helium-3. That's the lighter isotope of the much more abundant helium-4, which exists in the universe. And when it comes out of a nucleus in the form of alpha decay, then of course it's just the nucleus that comes out and then captures electrons to form a helium atom. So anyway, in this reaction,
you have 5 minutes.
Okay. So I think I will probably have to end somewhere. So I'll find a solution. So should I end right now? If there are questions, I'll end at the end of this slide, and then maybe I can take some questions. Murthy?
Sir, there are some questions, sir.
Yeah. Okay. So you can ask them right away.
Okay, sir. The question is it possible to explain the state of universe before Big Bang using quantum vacuum fluctuations?
Okay. Before the Big Bang, we really don't know. In fact, even just a little after the Big Bang, we have no clues as to what really took place. We have only theories, and there's no direct way of saying what happened at that time. But if you say before the Big Bang, that is, I think, in the realm of philosophy. We can only speculate. So what happened before that, we certainly cannot say on the basis of science. Even before the microsecond, before the Big Bang, we only have theories such as the inflation theory. Of course, it explains certain aspects of the universe. So maybe it will be proven to be correct from the observations that follow from the predictions of such a theory. But sort of post facto proof, or proof within quotes, you can never prove, of course, in science like in a theorem in mathematics. You can only say that, yeah, this is very likely to be true on the basis of evidence that you see. But before the Big Bang, I think it is just impossible.
Can I make a comment, Vivek?
Yes, sure.
I think we should assume that the time begins at the Big Bang.
Yeah.
So it means there's no before.
Yeah.
That is the present, state of our understanding of the universe. There are alternative theories, of course, the cyclical universe and all.
That's right.
But that's a different matter.
That's a different. So those are all speculative because we
Big Bang
don't know.
expansion, time begins at Big Bang.
Yeah. As far as we know, we can only tell what happened after the Big Bang.
The space-time, it comes into existence at the Big Bang.
Yeah. Now, whether, as you said, it is cyclical or whether it is not so, we don't really know.
We don't know.
And of course, from better measurements, we might be able to say whether the expansion of the universe will come to a grinding halt or not. Or maybe we will not be able to say that ever, because that is also a possibility.
Yes.
But, okay, so these are all the caveats. Okay, any other question?
Yes, sir. There is one more question.
Yes.
The question goes like this. Is there any possibility of finding single quark in any high energy explosions, even for a very small time, in the orders of minus 15 seconds or less, perhaps?
Okay, now the way we found evidence for these strange fractionally charged objects is through so-called deep inelastic scattering. Okay, and also through electron-positron collider experiments, where you found evidence for new quarks. And so you find that, when you look at electron-positron collider, I should say cross sections for producing hadrons, and you plot that as a function of energy, there are steps in this cross section when you start producing the heavier and heavier quarks. And these steps are actually related to the charges on these quarks. And they turn out to be in agreement with the fractional charges that we have assigned to quarks in these theories. For instance, QCD, quantum chromodynamics, the theory for strong interactions. Now, of course, but that doesn't mean that experimenters have not looked for fractional charges in nature. Because who knows, if experimentally you tomorrow find a fractional charge, then you will have to go back to the drawing board and construct theories which agree with the observation. In any case, people have looked for fractional charges, but have not to this day found evidence of any fractional charge in matter. So, for instance, the equivalent of the Millikan, the oil drop experiment has been done with superconducting objects. You can suspend them, and you can do all kinds of things. But we have found to this day no evidence. People have also looked for very exotic objects to look for these fractional charged objects. But nowhere have we yet found free fractionally charged object, evidence for that. Okay, we have only found evidence for fractionally charged objects in hadrons and in producing hadrons, for instance, or in deep inelastic scattering. Maybe Murthy might like to comment on that, if there is any other sort of evidence for fractionally charged.
It has always been indirect, and the best evidence is that E plus E minus collision that you talked about.
Yeah.
Because the whole cross section is proportional to charge squared.
Yeah.
So that comes into picture there.
Yeah.
So that is as direct as it comes. There's an indirect evidence in the production of top quark, because it doesn't form hadrons, but decays directly into hadrons.
Yeah.
Okay. So because it decays directly, we observe the decay directly. So that you can say, is actually a quark going directly into some other state.
Yeah.
Instead of hadronizing. But that's a little complicated way of saying it.
Yeah.
But E plus E minus collision is the best.
Yeah. So I think it was Fairbanks, probably, right? If I remember the name right. Fairbanks and also probably Cabrera, if I'm not wrong. Because Cabrera was looking at magnetic monopoles, but I don't know whether he
also fractional charges.
Fairbanks was trying to look for fractional charges and didn't find them
Yeah.
in a much improved version of the Millikan oil drop experiment.
Yeah. That's right.
Sir, there
Okay.
is
Any
one
other
more.
question?
Yes, sir, there is one more question.
Sure.
From Narasimha A. The question goes like this.
Yeah.
How the elements ratio is the evidence for Big Bang? With what accuracy?
With what accuracy? Okay. Now, uh, see, when you have theories uh, such as the Big Bang theory or let's say the steady state theory, they all make predictions. Okay. And they make strong predictions sometimes. Sometimes there are weak predictions. I would think that some of the strong predictions are, let's say, the cosmic microwave background. Then the way the nucleosynthesis occurred in the very early stages of the universe, and we actually have evidence for the ratios of these, synthesized elements of dating back to that time. That's one evidence. Then we have this anisotropy in the universe that we see in the black body radiation. It's not completely isotropic. There is still some structure in that, and that also can be understood within the theories that we have. So uh, we have fairly sort of. So I don't know whether this can be quantified, just like a particular measurement can be quantified in terms of confidence levels, or what is the chances that this is that you can really have the value above the values that you said to within 5 sigma and things like that. I don't know whether this can be. I don't think this can be quantified in that way. So we can't say with what accuracy, but we can certainly say that this. There is probably no other theory that competes with the Big Bang. At some point, maybe about 50, 60 years ago, the evidence was probably not so overwhelming for the Big Bang theory. So the steady state, in which, of course, Hoyle was the main proponent of that, but there are others who were also proposing that this be an alternate theory, uh, including our own Narlikar. Then there was, I think, a colleague of Hoyle in Oxford somewhere. So there were a few people, a few eminent scientists who were for
Vikramasinghe.
that. Huh?
Vikramasinghe.
Vikramasinghe. No, there is somebody else who was in Oxford, I think.
Yeah.
I forget the name. But in any case, they the steady state theory has problems they have they cannot probably understand so easily. They have to have a contrived explanation of all these observations of cosmic microwave background radiation, of let's say the primordial nucleosynthesis, of the structure formation, and so on, of the, the kind of observational data that we now have from Hubble and the radio astronomy data that we have. So I think taken as a whole, at least as an outsider, I believe that this is the theory that does best. There could be some things that may be predicted wrongly by the Big Bang, but then we will have to build on the Big Bang and make a theory which predicts all the correct things that Big Bang predicted, but also the new evidence that came out maybe in the subsequent years. So that's how, for instance, you take the example of Newton's theory of gravitation. When you are considering the motion of things which are moving at small velocities, Newton's theory is perfectly okay. But if you consider that the very strongly gravitating objects, or the fact that then you have a problem explaining that in Newton's theory, and so you have to go beyond that. Not that Newton's theory is wrong in the domain in which it was considered. It was theorized for. So you build on that. So if there is some observation that is at loggerheads with the Big Bang in some domain, then we will have to build on that and expand on that. Just as the present theory of Einstein, if there is some observation that points to quantum effects, which are not there in Einstein's theory, which is basically a classical theory, then we will have to take that into account. And already, of course, people are working on quantum versions of gravity. quantum gravity, and then of course the string theorists, of course, have theories on that front as well. Yeah, I hope that answers your question,
Yes, sir.
or at least partly answers your question.
There are no more questions, sir.
Yeah.
If there are any other questions, you can write back to us. We'll reply accordingly.
Yeah. Or
Thank you.
we are on Zoom. You can ask them yourself right now
Yes, sir.
instead of through the chat box.
Yes, sir.
Just we are muted all participants' audios, sir. They can't ask the questions directly because if we allowed to ask questions through the voice, then it will become a mess in the room, sir.
Okay.
That's why we
Because there will
muted.
be a lot of background noise if
Yeah,
people
it
don't
will
take care. Even if there are 2-3 people where the
yeah.
background is a lot. Yeah.
We
Okay.
can't control the people.
Okay.
Thank you, sir, for this informative session. It was a privilege to have you with us.
Thank you.
Tomorrow's lecture session link will be sent to your registered email IDs. Looking forward to see you all. Thank you all once again.
Will it not be the same link, or it will be a different link? Is it?
Same
It's
link, sir.
same link only. Again, we are going to send it to everyone.
Okay. Fine.
Okay. And it begins at 4:15, right?
Yes, sir. It begins at 4:15.
Hey, today, Murthy, you began a little earlier, is it? Because I
began a little earlier.
4:13 or something, and you had already started.
Correct.
Yeah, because we have to allow the participant to inside rooms, so that we began earlier.
Okay. So tomorrow it will start at
4:15.
Yeah, program will start exactly 4:15, sir.
Okay.
But we open room before 4:50, 4 o'clock.
Okay.
3:45, 4 o'clock, like that.
Okay.
Yeah. I would just like to, because when you're talking like this on video, you don't know, you don't get a feedback from the students whether it is going well or is not going well, is going overhead or is it too
Final day.
simple. So
Yeah, it's in the chat box, sir. There are comments regarding the everyday session.
Okay.
And also in final day, we are going to take feedback from each of the participants. Then we will know what's the feedback from the participant.
Okay, so that's an overall feedback. But I would also like a feedback if it is there.
Each session.
If there is any correction that I could do for the next talk, I would be happy to do that.
Yeah, we try to
Or
make
is
it
the space okay? I mean, the space is a little slow, I guess, but
yeah. Today we try to make find out that.
Okay.
Yeah,
thank you very much. Thank you very much.
Thank you, sir. Have a pleasant evening.
Thank you.